From the tiniest particles to the grandest structures, our universe is filled with mysteries that continue to baffle and inspire. What secrets lie hidden in the shadows of black holes? How did the first stars ignite the darkness of the early universe? Are we alone, or could there exist other life? Join us as we delve into some of the biggest mysteries in the universe that has puzzled scientists for centuries. Beneath the frosty exterior of Jupiter's moon, Europa lies a tantalizing possibility, a vast hidden ocean of liquid water. Europa, which is slightly smaller than Earth's moon, has intrigued scientists since the late 20th century, when data from missions like Voyager and Galileo hinted at this secret. The moon's ice shell is believed to be approximately 10 to 15 miles thick, but beneath this frozen crust, the water ocean could be over 60 miles deep, far surpassing the volume of Earth's oceans. The potential for liquid water is made even more compelling by the presence of chaotic terrains on Europa's surface, regions where ice appears to have been disrupted and refrozen, suggesting convection from below. Moreover, tidal forces exerted by Jupiter's immense gravity generate internal friction within Europa's core, producing heat that keeps the ocean from freezing solid. This intriguing combination of factors points to the possibility of a habitable environment where the essential ingredients for life, such as water, chemical nutrients, and energy sources, might converge in ways we are just beginning to understand. This has led to speculation and intensely focused scientific inquiry, as missions like the upcoming Europa Clipper aim to uncover more about this enigmatic moon. Enceladus, one of Saturn's most captivating moons, has left scientists abuzz with the possibility of extraterrestrial life within its icy confines. With a diameter of just 300 miles, Enceladus is relatively small, but it conceals a tantalizing secret beneath its frozen crust, an expansive subsurface ocean. This hidden ocean was first suggested by data from the Cassini spacecraft, which detected plumes of water vapor and icy particles erupting from fractures near the moon's south pole, known as tiger stripes. These geysers provide crucial clues about the ocean beneath, hinting at an environment that could potentially sustain life. The expelled material from Enceladus's geysers has been found to contain organic compounds, salts, and silica grains, suggesting chemical interactions between the ocean water and the moon's rocky core. These interactions could produce the energy necessary to support microbial life, similar to hydrothermal vents found on Earth's ocean floor. Moreover, the presence of hydrogen in the plumes indicates ongoing hydrothermal activity, a key ingredient for life as we know it. While scientists can't yet confirm the existence of life on Enceladus, the combination of water, organic molecules, and geothermal energy presents a compelling case. Future missions, equipped with sophisticated instruments, may one day pierce through Enceladus's icy shell to offer definitive answers. The hexagonal storm swirling around Saturn's North Pole is one of the most enigmatic weather phenomena in our solar system. First discovered by the Voyager spacecraft in the early 1980s, this geometric feature stretches roughly 14,000 miles across, large enough to encompass nearly 4 Earths. Unlike the more familiar round storms observed on Earth and other planets, Saturn's hexagon is a persistent and stable structure, baffling scientists with its precise angles and straight sides. The prevailing theory suggests that the hexagon is the result of a standing wave pattern in Saturn's atmosphere, similar to certain wave patterns observed in Earth's atmosphere and oceans. These waves are thought to be generated by the differential rotation of Saturn's atmosphere, where various jet streams flow at different speeds. At the direct influence of a particularly strong eastward jet stream, a phenomenon known as a Rossby wave could be propagating around the pole. This would create a series of interacting winds and vortexes that ultimately stabilize into the hexagonal shape. Additionally, observations from the Cassini spacecraft revealed that the hexagon extends deep into the atmosphere, up to nearly 200 miles below the cloud tops, suggesting that this unique storm is deeply rooted in Saturn's complex gaseous dynamics. The hexagon also changes color with the seasons, turning from a bluish hue to a golden tone, further indicating the rich interplay of atmospheric chemistry and solar radiation at Saturn's frigid poles. Venus, often dubbed Earth's sister planet due to its similar size and mass, defies expectations with its peculiar rotation. Unlike most planets in our solar system, which rotate counterclockwise when viewed from above their north poles, Venus spins in the opposite direction. This retrograde rotation means that on Venus, the Sun rises in the west and sets in the east. Additionally, Venus has an incredibly slow rotation, taking about 243 Earth days to complete one spin, making its day longer than its year. The exact reason for this backward rotation remains a subject of scientific debate, but several theories offer intriguing explanations. One prevalent hypothesis suggests that Venus experienced a colossal collision with another protoplanet, or a series of smaller impacts during the chaotic early history of the solar system. These cataclysmic events could have altered its rotation axis and direction. Another theory points to the effects of solar tides, where the immense gravitational pull of the Sun might gradually have slowed Venus's initial rotation and ultimately reversed it. The thick, dense atmosphere of Venus, which is 90 times more massive than Earth's, plays a role as well. Atmospheric tides caused by the extreme heat of its runaway greenhouse effect could interact with the planet's rotation, contributing to the retrograde motion. Simulations and models continue to refine our understanding, but the true cause of Venus's backward spin may combine elements of these theories. Each hypothesis adds a piece to the puzzle, gradually unraveling the complex dynamics that make Venus one of the most fascinating and mysterious bodies in our solar neighborhood. Mars' tiny moons, Phobos and Deimos, present a captivating mystery regarding their origins. These irregularly shaped satellites resembling asteroids more than traditional moons were discovered in 1877 by American astronomer Asaph Hall. Both moons are considerably small compared to Earth's moon, with Phobos spanning roughly 14 miles in diameter and Deimos about 8 miles. Their odd shapes and surface characteristics have led scientists to ponder how they came to orbit the red planet. One leading theory posits that Phobos and Deimos are captured asteroids from the asteroid belt between Mars and Jupiter. This hypothesis is supported by their composition, which is similar to that of carbonaceous chondrites, a type of asteroid rich in carbon. However, capturing an asteroid into a stable orbit is inherently difficult, making this scenario less straightforward and leading some scientists to explore alternative explanations. Another theory suggests that the moons may have formed from debris resulting from a massive impact on Mars. Such a collision could have launched material into orbit around Mars, which then coalesced to form Phobos and Deimos. This idea is bolstered by computer simulations that show how collision debris can accrete into moons. Additionally, the inner moon, Phobos, is gradually spiraling toward Mars and expected to disintegrate or crash into the planet within the next 50 million years, which aligns with the theory that these moons are not stable over the very long term. Although definitive evidence is still pending, missions like the proposed Martian Moons Exploration, MMX by JAXA, aim to uncover more insights by studying and possibly returning samples from these enigmatic moons. Such investigations could finally resolve the enduring question of their origins, adding another fascinating chapter to our understanding of Mars and its celestial neighbors. The unusual bright spots in Akator crater on Ceres have puzzled astronomers since they were first imaged by NASA's Dawn spacecraft in 2015. These bright deposits, most prominently located in the center of the crater, stand in stark contrast to the otherwise dark and heavily cratered surface of the dwarf planet, which lies in the asteroid belt between Mars and Jupiter. Detailed analysis has revealed that these spots are primarily composed of sodium carbonate, a type of salt, suggesting intriguing geologic activity on Ceres. The bright spots are believed to be the result of subsurface briny water reservoirs that have breached the surface. When this salty water ascends through fractures in Ceres' crust, it rapidly evaporates in the vacuum of space, leaving behind reflective salt deposits. This process indicates that, despite its frigid temperatures, Ceres possesses subsurface liquid kept from freezing entirely by residual internal heat or possibly by the presence of antifreeze-like substances. Furthermore, the geophysical models and data from Dawn imply that the Akator crater is relatively young, geologically speaking, having formed less than 30 million years ago. The impact that created the crater likely exposed subsurface water ice and caused subsequent hydrothermal activity, pushing the briny water upwards. This discovery on Ceres has profound implications for our understanding of the solar system's small bodies, as it suggests that even these seemingly inert objects might have the chemical processes necessary to harbor life, or at least prebiotic chemistry, in their past or present. The bright spots of a Kato crater are not just visually stunning, they are a beacon for ongoing exploration and study into the secrets held by the numerous worlds beyond Earth. Uranus presents one of the most striking peculiarities in our solar system, its extreme axial tilt of approximately 98 degrees. This unusual orientation means that Uranus essentially rolls along its orbit around the Sun, with its poles alternately facing the Sun directly every 84 Earth years. Understanding how this seventh planet from the Sun ended up in such an extraordinary position has intrigued scientists for decades. The prevailing hypothesis among astronomers is that Uranus's tilt resulted from a colossal collision. During the chaotic early days of the solar system, when planetary formation was tumultuous and violent, it is believed that Uranus experienced a collision with a protoplanet, or a series of massive impacts. These cataclysmic events could have knocked the planet onto its side, significantly altering its axial tilt. Computer simulations support this theory, demonstrating that such a dramatic tilt could be achieved by a collision with an object at least twice the size of Earth. Another aspect reinforcing this hypothesis is the existence of Uranus's moons and the peculiar orientation of its magnetic field, both of which align with the tilted rotational axis. This alignment suggests that not only Uranus but its entire system of moons and rings were likely affected by the same colossal event. Moreover, the planet's internal structure and unusual heat distribution further indicate a history of violent impacts. These pieces of evidence collectively weave a narrative of a world that once experienced a massive transformative collision, leaving Uranus as the unique tilted giant we observe today. Mercury, the closest planet to the Sun, experiences some of the most extreme temperature variations in our solar system. Unlike Earth, where temperatures are moderated by an atmosphere and oceans, Mercury lacks a substantial atmosphere, which is crucial for stabilizing surface temperatures. This deficiency plays a significant role in the dramatic thermal swings observed on the planet's surface. During the Mercurian day, which lasts approximately 59 Earth days due to the planet's slow rotation, surface temperatures can soar to a scorching 800 degrees Fahrenheit. This intense heat is primarily due to Mercury's proximity to the Sun, receiving more than 7 times the solar energy per unit area compared to Earth. The absence of a thick atmosphere means there is no medium to distribute this heat evenly across the planet, or to retain it once the Sun sets. As Mercury rotates and its long night begins, the surface rapidly loses heat, plunging temperatures to a frigid -330 degrees Fahrenheit. This drastic cooling occurs because there is no atmospheric insulation to trap the heat. The stark difference between day and night temperatures results from the planet's lack of atmospheric blanket that could moderate the heat flow between day and night regions. Interestingly, Mercury's extreme temperature variations also affect its geological features. The planet's surface is continually contracting and expanding due to these temperature changes, leading to the formation of cliffs and ridges. This dynamic contributes to Mercury's rugged and heavily cratered appearance. These temperature extremes and their effects offer a glimpse into the complex and harsh environment of the innermost planet in our solar system. The Great Red Spot, a colossal storm that has raged on Jupiter for at least 400 years, is gradually shrinking. This iconic feature, once large enough to swallow 3 Earths side by side, has diminished in size considerably over the past few decades. Scientists have been observing this phenomenon with keen interest, employing both Earth-based telescopes and spacecraft like NASA's Juno mission to understand the underlying causes of this enigmatic contraction. One significant factor contributing to the shrinking of the Great Red Spot is changes in Jupiter's atmospheric dynamics. The storm is essentially an anticyclone, a high-pressure system where winds circulate counterclockwise in the planet's southern hemisphere. Historically, the red spot's vorticity, or the rotation rate of this enormous vortex, has been decreasing. This decrease in rotational energy likely results in a weakening of the storm. Consequently, its size diminishes as it loses the battle against surrounding jet streams and atmospheric turbulence that can strip away its energy. Additionally, interactions with other Jovian atmospheric features also play a vital role. The Great Red Spot often encounters smaller neighboring storms and vortices, which can disrupt its structure and siphon off some of its energy. This complex interplay within Jupiter's dynamic atmosphere leads to the gradual erosion of the storm's boundaries. Observational data have shown that these interactions can physically fragment portions of the Great Red Spot, thereby contributing to its ongoing shrinkage. Although the Great Red Spot remains an extraordinary feature on Jupiter, its continued contraction suggests that even the most powerful storms in the universe are subject to the ever-changing forces of their environments. The phenomena driving the shrinkage are a testament to the dynamic and evolving nature of planetary atmospheres and highlight the intricate interplays that govern the behavior of such immense weather systems. Neptune, the distant and icy giant of our solar system, harbors a fascinating and exotic feature deep within its interior, the so-called hot ice layer. This intriguing term refers to water ice that exists under extreme pressure and temperature conditions, vastly different from the everyday ice we encounter on Earth. Neptune's internal structure is thought to consist of a rocky core surrounded by a thick layer of water, ammonia, and methane ices, enveloped by an outer layer of hydrogen and helium atmosphere. The hot ice layer on Neptune is composed predominantly of water, H2O, but in a state unlike any ice found on the terrestrial surface. At pressures millions of times greater than Earth's atmospheric pressure and temperatures reaching thousands of degrees, water molecules in Neptune's interior are compacted into exotic crystalline structures known as superionic ice. In this state, the oxygen atoms form a lattice structure, while the hydrogen ions move freely within this lattice, creating a form of ice that is both solid and fluid-like. These conditions lead to unique physical properties, such as high electrical conductivity and increased density compared to normal ice. Laboratory experiments on Earth using tools like diamond anvil cells and high-energy lasers have managed to recreate these extreme conditions, providing insights into the properties of superionic ice. These studies suggest that within Neptune's hot ice layer, the ice remains solid due to the immense pressures, even though the temperatures are high enough to melt conventional ice. Additionally, the presence of ammonia and methane can further influence the formation and stability of these exotic ices, potentially creating complex compounds not found naturally on Earth. Understanding Neptune's hot ice layer gives scientists a deeper glimpse into the physics of planetary interiors and the composition of ice giants. It also expands our knowledge of how diverse and intricate planetary processes can be, particularly in the harshest environments of our solar system. This research has implications for the study of exoplanets as well, suggesting that similar ices could exist on other distant ice-rich worlds far beyond our own. WASP-12b is an exoplanet that stands out not just for its extreme conditions, but also for its remarkably dark appearance. Discovered in 2008, WASP-12b orbits its host star so closely that it completes a revolution in merely 1.1 days. This close proximity means the planet is subjected to intense stellar radiation, heating its atmosphere to scorching temperatures exceeding 4,000 degrees Fahrenheit. Such extreme conditions have intriguing implications for the planet's physical characteristics, especially its albedo or reflectivity. The primary reason WASP-12b is one of the darkest known exoplanets lies in its atmosphere's unique composition and its interaction with the intense radiation from its star. Unlike more reflective planets, WASP-12b absorbs almost all of the light that hits it, reflecting back less than 6%, making it even darker than fresh asphalt. This extraordinary absorptive capability is largely due to the presence of atoms and molecules like titanium oxide, vanadium oxide, and iron hydrides in its atmosphere. These compounds are highly efficient at absorbing visible light, trapping the stellar energy and converting it to heat rather than reflecting it away. Compounding this dark appearance, the extreme heat on WASP-12b also prevents the formation of reflective clouds or hazes that are commonly found in the atmospheres of other gas giants. Without these reflective layers, the planet lacks the bright, shiny clouds that would otherwise bounce light back into space. Observations from the Hubble Space Telescope and other instruments have been crucial in identifying these absorptive materials and understanding the complex atmospheric dynamics at play. The study of WASP-12b continues to offer valuable insights into the wide variety of atmospheric conditions that can exist on exoplanets and the mechanisms that give rise to such dark, light-absorbing worlds. WASP-12b's exceptional darkness provides a stark contrast to the more familiar reflective gas giants in our solar system, showcasing the extraordinary diversity present in planetary systems across the cosmos. HD 189733b, a vivid blue exoplanet located 63 light-years away in the constellation Vulpecula, provides a striking contrast to Earth despite its similar azure hue. Unlike Earth, where the blue color of the sky comes from Rayleigh scattering of sunlight by the atmosphere, the blue tint of HD 189733b is due to its exotic weather conditions and atmospheric composition. This scorching hot Jupiter, which orbits very close to its host star, experiences surface temperatures of around 1,800 degrees Fahrenheit, leading to some truly otherworldly phenomena. One of the most fascinating aspects of HD 189733b's atmosphere is the presence of silicate particles and condensed metals, such as magnesium silicate, in its upper atmosphere. These tiny particles can form clouds and rain droplets of molten glass. When these glass particles fall through the atmosphere, they scatter blue light more effectively than other wavelengths due to their size and the specific optical properties of silicates, which results in the planet's distinctive blue coloration. Moreover, the extreme atmospheric conditions on HD 189733b lead to high-speed winds, estimated to blow at over 4,300 miles per hour. These intense winds would make the falling molten glass rain a horizontal torrent, adding to the planet's hazardous environment. The combination of high temperatures, silicate-rich clouds, and violent winds creates a unique system where blue-colored rain of molten glass hurtles through the atmosphere. This not only contributes to the planet's blue appearance, but also highlights the diversity of planetary weather systems and the complex interactions between atmospheric chemistry and local conditions in exoplanetary environments. As instruments and observational techniques advance, further studies of such exotic worlds will continue to expand our understanding of the varied and often extreme climates that exist beyond our solar system. The concept of diamond rain on Neptune and Uranus is one of the most fascinating phenomena in planetary science. This otherworldly weather is driven by the unique conditions found deep within these ice giants. Both planets possess a thick atmosphere composed primarily of hydrogen and helium with substantial amounts of methane, ammonia, and water. It is the presence of methane in particular that sets the stage for this extraordinary meteorological event. Methane molecules consist of one carbon atom bonded to 4 hydrogen atoms. Under the extreme pressures and temperatures found thousands of kilometers below the surface of Neptune and Uranus, around 7,000 degrees Fahrenheit, the methane is believed to break apart. Here, the intense environmental conditions cause the carbon atoms to be released from the methane molecules. As the pressures increase, these free carbon atoms are squeezed together into crystalline structures forming diamonds. These diamonds then rain down through the planet's interiors, falling potentially thousands of kilometers. This diamond rain isn't just a poetic idea, it's supported by experimental evidence from labs on Earth. Scientists using high-pressure devices like shock compression techniques have successfully recreated the extreme conditions of the deep interiors of Neptune and Uranus. These experiments show that under such intense pressure, carbon indeed forms diamond-like structures. Moreover, the presence of diamond rain suggests a dynamic and active interior for these ice giants. As diamonds descend toward the planet's cores, they generate frictional heat, which may contribute to the thermal profile and possibly the magnetic fields of Neptune and Uranus. This phenomenon underscores the exotic and diverse nature of planetary processes, illustrating how different worlds can exhibit behaviors that are almost unimaginable within the context of our own earthly experience. Understanding these mechanisms not only enriches our knowledge of Neptune and Uranus, but also offers insights into the possible interior dynamics of exoplanets with similar compositions, expanding our grasp of planetary science across the galaxy. Kelt 9b is an extraordinary exoplanet that shatters many conventional notions about planetary climates. Discovered in 2016, this gas giant orbits its star, Kelt 9, a luminous A-type star, every 1.5 days. Due to its extremely close proximity to its host star, Kelt 9b endures one of the harshest environments known, with its dayside temperature soaring to a blistering 7,800 degrees Fahrenheit. This incredible heat makes the dayside of Kelt 9b hotter than some stars, including red dwarf stars, which typically have surface temperatures around 6,000 degrees Fahrenheit. Several factors contribute to Kelt 9b's extreme thermal environment. Firstly, the planet orbits at a mere 3.4 million kilometers from its host star, significantly closer than even Mercury is to the Sun. This tight orbit exposes Kelt 9b to an immense amount of radiant energy from its star, which is itself much hotter and more massive than our Sun. The star Kelt 9 emits a substantial amount of ultraviolet radiation, further contributing to the high-energy bombardment of the planet's atmosphere. Additionally, Kelt 9b is tidally locked, meaning one side of the planet constantly faces the star while the other side remains in perpetual darkness. This results in a significant temperature gradient between the day side and the night side. The intense stellar radiation on the day side prevents any cool down during the night, leading to extreme heating and energetic processes in its atmosphere. The planet's atmosphere is composed of hydrogen and other elements that get ionized and dissociated under such high temperatures, creating a plasma-like environment. Observations also suggest that these extreme conditions lead to complex atmospheric dynamics, including strong winds that redistribute some of the heat around the planet. The study of Kelt 9b offers profound insights into the physics of exoplanets under extreme conditions and showcases the diverse and often surprising nature of planetary science. Understanding these high-temperature environments extends our knowledge of planet-star interactions and the potential atmospheric compositions that can result, enriching our broader comprehension of exoplanetary systems throughout the galaxy. Imagine a world where the sky hosts not one but two suns, dancing around each other in an intricate celestial ballet. This is the reality for Kepler 16b, a planet situated 200 light-years away from Earth, that orbits not just one but two stars. This type of phenomenon is known as a circumbinary planet, a marvel in the cosmos where a single planet orbits a pair of stars. Kepler 16b, roughly the size of Saturn, showcases how intricate gravitational forces can orchestrate stability amid what seems like chaos. The two suns it orbits are a pair of stars locked in a tight gravitational dance, completing an orbit around each other every 41 days. But how does this planet manage such a feat without being torn apart by the conflicting gravitational pulls of its twin suns? The answer lies in the delicate balancing act of gravitational forces and orbital resonance. The two stars create a combined gravitational field rather than individual ones, permitting Kepler 16b to travel in a stable path around the barycenter of this dynamic duo. This barycenter is the point around which the stars themselves orbit, generating a more unified force that acts on the planet. Despite its distance, circling the stars at a distance equivalent to the orbit of Venus around our Sun, Kepler 16b remains in a stable orbit thanks to this complex interplay of forces. The planet's stable yet extraordinary journey around two suns expands our understanding of the possible configurations in our ever-mysterious universe. Dubbed Methuselah after the biblical figure reputed for his long life, the planet PSR B 1620-26b stands as a celestial testament to the longevity possible in the cosmos. This ancient world orbits a unique duo of dead stars, a pulsar and a white dwarf. Methuselah's age, estimated to be around 12.7 billion years, makes it one of the oldest planets ever discovered. But what factors contribute to this extraordinary age? For most planets, their life cycle is intimately tied to the life cycle of their parent stars. Methuselah, however, found itself in an exceptional scenario. Formed in the early universe, it originally orbited a main sequence star, much like our Sun. But as the universe aged, changes occurred. The star evolved into a red giant and finally into a white dwarf. Later, the planetary system encountered a pulsar, a type of neutron star known for its rapid rotation and intense magnetic field, due to the gravitational interactions within the densely packed environment of its home, the globular cluster M4. This stellar encounter led Methuselah to adopt a new, albeit unusual, cosmic relationship with the pulsar and white dwarf. The stability within the dense globular cluster and the ancient origin of its stars collectively hint at Methuselah's incredible age. In this cosmic interplay, the planet's continued orbit around these stellar remnants through time essentially grants it the age it holds today, providing a fascinating glimpse into the early universe. WASP 107b, intriguingly known as a superpuff planet, exhibits characteristics that challenge our traditional understanding of planetary formation. Situated about 212 light-years from Earth in the constellation Virgo, WASP 107b is approximately the size of Jupiter, but is uniquely over 10 times less dense. To picture this anomaly, imagine a planet with the girth of our gas giant, yet possessing the mass closer to that of a smaller, icy planet like Neptune. The extraordinary formation of WASP 107b hints at an unconventional path in the planet-building processes. The perplexing nature of WASP 107b can partly be explained by its atypically massive, extended atmosphere. During its formative years, in the protoplanetary disk surrounding its star, the core of WASP 107b might have accumulated a significant amount of gas before substantial planetary migration occurred. Yet its core mass, much smaller than expected for the amount of gas enveloping it, suggests an unusual efficiency in gas accretion. It's as though it efficiently captured and held this massive atmosphere despite a relatively modest initial core. Additionally, its close orbit, positioned merely 8 million kilometers from its star, may contribute to the bloated nature of its atmosphere through the process of atmospheric inflation, driven by the star's intense heat. These factors combined, efficient gas capture by a smaller than expected core and the contribution of stellar heat, have ensured WASP 107b's designation as a superpuff planet. This celestial oddity not only invites deeper inquiry into the diversity of planetary systems, but also challenges existing models of gas giant formation, expanding our comprehension of the myriad ways in which planets can evolve and thrive in the universe. HD 189733b, a gas giant located 64 light-years away in the constellation Vulpecula, is a world of extremes. Its weather patterns are nothing short of astonishing, characterized by howling winds reaching speeds of up to 5,400 miles per hour. To put that into perspective, these winds blaze at speeds nearly 7 times that of the fastest hurricanes on Earth. This tempestuous activity finds its roots in the planet's close proximity to its parent star and the resulting dramatic temperature differences across its surface. Classified as a hot Jupiter, HD 189733b orbits its star at a blistering pace, completing one orbit in just over 2 Earth days. The planet is tidally locked, beholden to the same fate as our Moon with the Earth, showing the same face to its Sun at all times. This locked orientation results in an intensely heated dayside and a significantly cooler nightside, creating an environment ripe for extreme atmospheric dynamics. Temperatures on the dayside soar beyond 1,200 degrees Celsius, while the nightside experiences relatively cooler conditions. The stark temperature gradient between the two hemispheres generates fierce winds that rush from the blistering dayside to the cooler nightside in a desperate attempt to balance the thermal disparity. Additionally, HD 189733b's atmosphere, rich in silicate particles, may further accentuate these dramatic winds. As the intense heat from the star causes these silicates to vaporize, they form clouds that could potentially drive even more vigorous atmospheric circulation. The combination of extreme heat, rapid rotation, and silicate vapor clouds contributes to some of the most ferocious winds known in our cosmic neighborhood, illustrating the tumultuous and dynamic realities of weather on distant exoplanets. Planets like Coro 7b present a fascinating enigma, as they seem to defy the brutal conditions associated with their proximity to their parent stars. Located approximately 489 light-years away in the constellation Monoceros and orbiting its star in just over 20 hours, Coro 7b is classified as a lava world. This designation arises from the scorching temperatures resulting from its incredibly close orbit, which takes it roughly 23 times nearer to its star than Mercury is to the Sun. Such an extreme orbit initially raises questions about the planet's survivability. The endurance of Corot 7b in this hellish environment can be attributed to several key factors. First, its composition plays a crucial role. Unlike gas giants that would likely dissipate under such intense heat, Corot 7b is a rocky planet. Its solid nature, comprising metals and silicates, provides a resilience that gas giants lack. Despite surface temperatures exceeding 2,000 degrees Celsius on the star-facing side, which are hot enough to melt rock, Corot 7b remains intact thanks to its robust makeup. The planet's dense core, rich in heavy elements, offers the necessary gravitational hold to withstand the stellar onslaught. Additionally, the possibility of strong magnetic fields might help in shielding the planet's atmosphere, although the exact nature and extent of Corot 7b's magnetic field remain areas of active research. The intense proximity to its star means that any atmosphere it once had might have been blown away by the stellar winds, leaving a naked, rocky core. Survival then becomes a matter of stasis rather than thriving. The planet endures through sheer resilience against the continuous barrage of radiation and heat. This ability to persist close to a star offers a stark testament to the range of planetary adaptability, widening our understanding of the diverse conditions under which planets can exist. Corot 7b's survival in such severe circumstances challenges our preconceived boundaries of planetary habitability and endurance. Gliese 436b, a Neptune-sized exoplanet orbiting the red dwarf star Gliese 436 about 30 light-years away in the constellation. Leo presents a captivating puzzle with its peculiar atmospheric and temperature characteristics. Despite surface temperatures soaring to over 800 degrees Kelvin, Gliese 436b intriguingly maintains a significant amount of water ice. This paradox of a hot ice exoplanet has long confounded scientists and sparked curiosity about the physics underlying its atmosphere. The key to understanding this phenomenon lies in the extreme pressures at play within the planet. Gliese 436b's considerable gravitational pull forces water into a phase known as Ice 7, or superionic water. Here, the water molecules are densely packed due to the immense pressure, causing them to remain solid despite the searing temperatures. Effectively, the planet hosts a form of water ice that wouldn't typically exist under Earth's atmospheric conditions, defying our conventional expectations of states of matter. Adding another layer of intrigue are the emissions and potential atmospheric compositions. Observations suggest that Gliese 436b possesses an atmosphere rich in hydrogen, which could contribute to its heat retention, while the underlying high-pressure ice remains solid. Additionally, the feasibility of methane and other volatiles in the atmosphere presents a further anomaly, given that such compounds often break down at the temperatures observed. The planet's unique atmospheric properties suggest a complex interplay of gravitational compression, chemical composition, and heat transfer, making Gliese 436b an extraordinary laboratory for examining the limits of planetary physics. This unusual concoction of circumstances redefines our understanding of gas giants and ice giants alike, pushing the boundaries of what planetary atmospheres and surfaces can withstand. At the heart of our Milky Way lies an awe-inspiring and formidable entity known as Sagittarius A*, a supermassive black hole. Astronomers have identified this colossal object by observing its profound gravitational effects on nearby stars and gas clouds. Sagittarius A* itself remains invisible because no light can escape its intense gravitational pull, but the energetic dance of matter around it offers compelling evidence of its presence. This cosmic behemoth boasts a mass approximately 4 million times that of our Sun, compressed into a region no larger than the orbit of Mercury, an extraordinary testament to the mysterious and powerful nature of black holes. The environment surrounding Sagittarius A* is nothing short of extreme. As gas and dust swirl towards the black hole, they form an accretion disk, heating up to millions of degrees due to intense friction and gravitational energy. This superheated material emits X-rays and other high-energy radiation that astronomers detect using space-based observatories. The immense gravitational forces also catapult stars into high-speed orbits, some reaching velocities of up to several thousand kilometers per second. The study of these S-stars in close orbits around Sagittarius A** has been crucial in pinpointing not only the mass, but also the location of this supermassive black hole. In addition, recent detections of flares and sudden bursts of radiation from the region hint at even more dramatic interactions occurring just outside the event horizon, the boundary beyond which nothing can escape. These observations provide a captivating yet incomplete picture, driving scientists to push the boundaries of technology and theory to understand the complexities of galactic centers. As we continue to probe Sagittarius A*, we edge closer to unlocking the secrets not just of our own Milky Way, but of black holes and galactic cores throughout the universe. The formation of supermassive black holes, enigmatic giants anchoring the hearts of galaxies, remains one of the most fascinating and complex puzzles in astrophysics. These titans, with masses ranging from millions to billions of times that of our Sun, likely have multifaceted origins, drawing from several proposed mechanisms, each contributing to the grand cosmic tapestry. One prominent theory is that supermassive black holes formed from the collapse of massive primordial gas clouds in the early universe. These gas clouds, bereft of metals and other elements that would radiatively cool and fragment the collapsing material, could circumvent the usual star formation process, collapsing directly into black holes with masses on the order of thousands of solar masses. Such direct collapse black holes could then rapidly amass more material, growing to supermassive sizes in a relatively short cosmological time span. Another exciting pathway involves the merger and accretion processes occurring in dense stellar environments. In the crowded cores of young galaxies and protogalaxies, frequent collisions and mergers of massive stars could lead to the creation of intermediary mass black holes. These black holes would then sink to the galaxy's center due to dynamical friction, interacting gravitationally with less massive stars, and subsequently merging to form a supermassive black hole. Once situated at the galactic core, the black hole would continue to grow by feeding on gas, stars, and even other black holes through a process known as accretion. Moreover, the recent observations of gravitational waves have unveiled the role of hierarchical mergers, a process where black holes merge repeatedly over cosmic time, creating increasingly massive black holes. These multifaceted processes, direct collapse, accretion, and hierarchical mergers, likely worked in concert to produce the supermassive black holes we observe today. By delving into these formation theories, astronomers can piece together the evolutionary history of these cosmic giants, shedding light not just on the black holes themselves, but also on the galaxies they inhabit, offering a broader understanding of our universe's dynamic and intriguing nature. The Cartwheel Galaxy presents a mesmerizing visual of cosmic artistry, displaying a unique wheel-like appearance that sets it apart from typical galaxy formations. This extraordinary structure is primarily the result of a dramatic galactic collision, a cataclysmic event that unfolded hundreds of millions of years ago. The key to understanding the Cartwheel Galaxy's unusual shape lies in its violent past and the ensuing gravitational interactions. Located about 500 million light-years away in the constellation Sculptor, the Cartwheel Galaxy once likely resembled a standard spiral galaxy. However, it underwent a transformative encounter when a smaller galaxy barreled through its core. This high-speed collision sent powerful ripples of gravitational shockwaves radiating outward, much like the ripples seen when a stone is tossed into a pond. These waves compressed the interstellar gas and dust, triggering a wave of new star formation that spread outwards in a ring-like fashion from the point of impact. The result of this colossal interaction is a distinct ring of hot, young stars encircling the galaxy's center, giving the Cartwheel Galaxy its iconic appearance. This ring is generally referred to as a starburst ring because of the intense star formation it's witnessing. Compounding the central ring are the galaxy's spiral arms, now distorted and elongated due to the gravitational forces at play. The remnants of the impacted galaxy and possibly some of its stars have likely been flung into the outskirts or even merged with the Cartwheel Galaxy. Further observations using multi-wavelength astronomy, spanning X-rays, ultraviolet, optical, and infrared light, reveal the dynamic processes in the Cartwheel Galaxy's core and its outer ring. These insights illustrate the dramatic and complex nature of galactic interactions, where colliding galaxies can dramatically reshape and redefine their structure, resulting in the celestial masterpieces like the Cartwheel Galaxy. Galaxies like NGC 1277, often referred to as red and dead galaxies, are fascinating relics from an earlier era of the universe. Located around 220 million light-years away in the Perseus cluster, NGC 1277 is notable for its population of old stars, with little evidence of recent star formation. This ancient stellar composition offers a glimpse into the history of galaxy formation and evolution. The formation of such galaxies is thought to occur in stages, influenced by both intrinsic properties and external factors. In the early universe, NGC 1277 likely underwent a rapid and intense period of star formation, catalyzed by the abundant gas reservoirs available during that epoch. This period, known as a starburst phase, would have consumed substantial amounts of gas in a relatively short time, producing a dense, compact galaxy filled with massive young stars. These early bursts of star formation resulted in the production of many of the heavy elements present in the galaxy today. However, what set NGC 1277 apart is the relatively quick cessation of star formation. Several mechanisms could explain this quenching process. One possibility is that the galaxy exhausted its gas supply during the starburst phase, leaving little material for new stars to form. Another factor could be environmental influences, such as interactions within the dense Perseus cluster. NGC 1277 might have experienced gravitational encounters with other galaxies or the hot intra-cluster medium, stripping away its remaining gas through a process known as ram pressure stripping. Additionally, supermassive black holes residing at the centers of galaxies like NGC 1277 can play a crucial role. These colossal entities can heat the surrounding gas through energetic outflows and radiation, preventing it from cooling and collapsing to form new stars. This process, known as feedback, can effectively quench further star formation. As a result, NGC 1277 transitioned into a phase dominated by its old stellar population. These stars, formed billions of years ago, now constitute the majority of the galaxy's mass, giving NGC 1277 its characteristic appearance dominated by older red-hued stars. Studying such galaxies helps astronomers understand the evolutionary pathways that galaxies can take, shedding light on the various processes that can lead to the cessation of star formation and the maturation of galaxies over cosmic time. The immense voids in the cosmic web, vast expanses of nearly empty space, are among the most compelling features of the universe's large-scale structure. These voids can span tens to hundreds of millions of light-years, contrasting sharply with the dense clustering of galaxies along filaments and nodes. The formation of these colossal voids is fundamentally tied to the intricate interplay of gravity and the initial conditions set by the Big Bang. In the moments following the Big Bang, the universe was a hot, dense sea of nearly uniform matter and radiation. Tiny density fluctuations caused by quantum perturbations during inflation, a rapid expansion of the universe, seeded regions of slightly higher and lower densities. As the universe expanded and cooled, these initial fluctuations snowballed under the influence of gravity. Over time, areas of higher density began to collapse and form galaxies and galaxy clusters, anchoring the cosmic web's filaments and nodes. Meanwhile, regions of slightly lower density evolved in the opposite direction. Lacking sufficient mass to halt their expansion or initiate significant gravitational collapse, these regions progressively emptied out as matter flowed away toward the denser areas. Consequently, the lower density patches expanded into the vast voids we observe today, creating the immense empty spaces amidst the interconnected filaments of galaxies. Dark energy, a mysterious force driving the accelerated expansion of the universe, further plays a role in the evolution of cosmic voids. As dark energy propels the overall expansion of space, it accelerates the evacuation of matter from these underdense regions, making the voids even emptier over time. Additionally, simulations of cosmic structure formation utilizing the principles of dark matter and dark energy, have effectively reproduced the observed distribution of voids. These simulations underscore the critical role dark matter, comprising about 85% of the universe's mass, plays in structure formation. Dark matter, interacting gravitationally but not electromagnetically, guides ordinary matter to clump along the cosmic web, sculpting the vast voids amid the grand structures. By studying these immense voids, astronomers gain valuable insights into the universe's composition, its expansion history, and the fundamental forces shaping its evolution. The cosmic voids serve as a counterpoint to the densely populated regions, offering a complementary perspective on the universe's large-scale structure and the dynamics at play across vast cosmic timescales. Galactic filaments, the immense tendrils of galaxies and dark matter that define the cosmic web, present a remarkable example of the universe's large-scale structure. These colossal formations span hundreds of millions of light-years and form a complex network of nodes and intersections where galaxy clusters reside. The maintenance of these structures over cosmic timescales hinges on several fundamental factors, including gravity, dark matter, and the ongoing interaction with surrounding cosmic environments. At the heart of the filament's stability lies the gravitational pull exerted by dark matter. Accounting for about 85% of the universe's total mass, dark matter does not emit or interact with electromagnetic radiation, making it invisible and detectable only via its gravitational effects. This unseen component forms the scaffold on which ordinary matter, baryonic matter, clumps together to form galaxies and galaxy clusters. As dark matter congregates along the filaments, it creates gravitational wells that draw in and hold regular matter, reinforcing the filamentary structures. Einstein's theory of general relativity further explains how massive objects warp space-time, contributing to the gravitational dynamics that maintain the form of these vast filaments. The interplay of gravitational forces ensures that matter flowing through the cosmic web tends to aggregate along these potential wells, continually feeding and reinforcing the filaments. Moreover, the universe's expansion, driven by dark energy, subtly influences these cosmic megastructures. While dark energy propels the accelerated expansion of space, its effect varies with scale. On larger scales, such as between superclusters, dark energy leads to accelerated expansion, pushing structures apart. However, within individual filaments, the gravitational forces from dark matter and baryonic matter dominate, binding the structures together and counteracting the expansive push of dark energy, thus preserving the integrity of the filaments over billions of years. Additionally, ongoing galaxy formation and interactions play a pivotal role. Galaxies within these filaments can experience mergers and accretion, which redistribute matter along the filaments and clusters. These interactions contribute to the dynamical processes that maintain the coherence of the filamentary structure, even as individual galaxies evolve. Finally, advanced cosmological simulations powered by highly sophisticated computational models have extensively validated these processes. These simulations incorporate dark matter, baryonic matter, gravity, and dark energy to replicate the observed large-scale structure of the universe. The consistency between these theoretical models and actual astronomical observations underscores the robustness of these mechanisms in maintaining the galactic filaments. Through the symbiotic interplay of gravity, dark matter, and cosmic dynamics influenced by dark energy, galactic filaments endure, giving us a window into the universe's grand design, stretching across cosmic time and space. The periodic structure of the universe on ultra-large scales, often referred to as the cosmic web, reveals itself through a stunning arrangement of galaxies, clusters, and superclusters, interconnected by vast filaments and interspersed with enormous voids. This grand architecture is not random but rather a well-organized structure that reflects the underlying physical processes that shaped the universe following the Big Bang. The roots of this periodicity can be traced back to the early universe, particularly during the epoch of inflation, a brief period of exponential expansion that occurred fractions of a second after the Big Bang. Inflation stretched tiny quantum fluctuations to macroscopic scales, seeding regions of varying densities in the primordial plasma. These primordial density fluctuations serve as the blueprint for the large-scale structure we observe today. As the universe continued to expand and cool, these initial density variations translated into areas of slightly different matter concentrations. The force of gravity caused the denser regions to attract more matter, growing into galaxies, galaxy clusters, and superclusters, while less dense regions became the vast cosmic voids. This process of gravitational collapse and clustering over billions of years gave rise to the interconnected cosmic web structure. A pivotal phenomenon contributing to this structure is known as baryon acoustic oscillations, BAOs. In the early universe, the interplay between matter and radiation created sound waves that propagated through the hot, dense plasma. These oscillations left imprints in the distribution of matter when electrons and protons combined to form neutral hydrogen, allowing radiation to decouple and escape as the cosmic microwave background. The characteristic scale of these acoustic waves now manifests as a slight preferential separation between galaxies, providing a standard ruler for cosmological measurements. Dark matter, making up about 27% of the universe's total mass energy content, further plays an indispensable role in shaping the periodic structure. Dark matter does not interact with light but exerts gravitational influence, forming a scaffolding that guides the clumping of normal matter, baryonic matter. Through processes governed by gravity, regions rich in dark matter became sites for galaxy formation, reinforcing the periodic patterns set by the primordial fluctuations and BAOs. Dark energy, constituting about 68% of the universe, influences the large-scale structure by driving the accelerated expansion of the universe. While dark energy tends to push structures apart on the largest scales, its impact is more pronounced in the vast voids between the filaments and clusters, subtly altering the periodic arrangement over cosmic time. In combining observations from telescopic surveys and simulations, scientists find a congruence between theoretical models and actual data, confirming the periodic structure of the cosmic web. These models integrate the effects of inflation, BAOs, dark matter, and dark energy, offering a coherent picture of how the universe's large-scale periodic structure originated and evolved, presenting a remarkable testament to the underlying unity and complexity of cosmic evolution. Galaxy clusters like El Gordo, whose name translates to the Fat One in Spanish, are among the largest and most massive structures in the universe. Located approximately 7 billion light-years away, El Gordo is an extraordinary example of a galaxy cluster, boasting a mass roughly 3 quadrillion times that of the Sun. The formation of such colossal clusters is a testimony to the intricate processes of cosmic evolution, governed primarily by the interplay of gravity, dark matter, and dark energy. The formation of El Gordo and galaxy clusters in general begins with the gravitational collapse of dark matter in the early universe. Dark matter, which makes up about 85% of the universe's matter, doesn't interact with electromagnetic radiation, so it remains invisible, detectable only through its gravitational effects. In the aftermath of the Big Bang, dark matter began to clump together under the influence of gravity, forming halos that acted as gravitational wells. These dark matter halos attracted baryonic matter, ordinary matter composed of atoms, leading to the formation of galaxies within them. Over time, smaller halos merged to form larger aggregates, a process known as hierarchical clustering. Through repeated mergers and accretions, these massive structures coalesced into the galaxy clusters we observe today. El Gordo is thought to have formed through the collision and merging of 2 smaller galaxy clusters, an energetic process that creates shockwaves observable in various wavelengths, including X-rays. Strong evidence for El Gordo's formation through such a collision comes from observations of its hot intra-cluster gas. El Gordo's gas emits X-rays detected by telescopes like NASA's Chandra X-ray Observatory. These observations reveal a turbulent distribution of hot gas, indicative of a high-energy collision. The gas in El Gordo is extremely hot, reaching temperatures of tens of millions of degrees, and it exhibits shock waves and compression features that are telltale signs of massive cluster mergers. Moreover, the distribution of dark matter within El Gordo has been mapped using gravitational lensing, a phenomenon predicted by Einstein's general relativity, where massive objects warp the fabric of space-time, bending and magnifying the light from more distant objects. These gravitational lensing observations show an extended, clumpy distribution of dark matter, further supporting the scenario of a recent and violent collision between galaxy clusters. Dark energy, the mysterious force driving the universe's accelerated expansion, also plays a role, though more subtly. While dark energy tends to push galaxy clusters apart on the largest scales, within the clusters themselves, gravitational forces dominate. The accelerated expansion due to dark energy affects the rate at which galaxy clusters can grow, limiting how quickly they can attract additional material from substructures. El Gordo's immense mass and dynamic nature provide a crucial observational anchor for testing cosmological theories and models. By studying such galaxy clusters, astronomers gain insights into the nature of dark matter, the effects of dark energy, and the processes of galaxy formation and evolution over cosmic time. Observations of El Gordo and similar clusters help refine our understanding of the universe's large-scale structure and the forces shaping its evolution. High-velocity clouds, HVCs in galactic halos, present an intriguing and complex puzzle in the field of astrophysics. These massive concentrations of gas exhibit velocities that significantly differ from the regular rotational movement of their host galaxies. The exact origins of HVCs are multifaceted, involving several potential sources and processes that contribute to their presence in the galactic halo. One prominent theory suggests that HVCs originate from the galactic fountain mechanism. In this process, ongoing star formation and supernova explosions within a galaxy's disk generate powerful stellar winds and shock waves that eject gas into the galactic halo. As this gas cools and loses energy, it eventually falls back toward the galaxy's disk, sometimes at high velocities. This cycling of gas between the disk and halo plays a critical role in regulating star formation and redistributing chemical elements within the galaxy. Another possible source of HVCs is gas accretion from the intergalactic medium, IgM. Galaxies are not isolated systems. They continually interact with their surrounding environments. Cold gas from the IgM can be pulled into a galaxy's gravitational influence, streaming toward the halo at high velocities. This infalling gas can replenish the galaxy's star-forming material and contribute to the overall growth and evolution of the galaxy. HVCs may also result from the tidal interactions and mergers between galaxies. When galaxies encounter each other, their gravitational fields can distort and strip away gas from their disks, flinging it into the halo at high velocities. These interactions are particularly common in galaxy clusters, where galaxies move through a dense intergalactic environment and frequently interact with each other. Furthermore, high-velocity clouds could be remnants of earlier galaxy formation processes. During the early stages of a galaxy's evolution, gas clouds that did not form stars could remain in the galactic halo, maintaining high velocities due to the initial conditions of their ejection or collapse. Observational evidence for these theories comes from a variety of sources, including radio observations of neutral hydrogen using facilities like the Arecibo Observatory and the Green Bank Telescope. These observations reveal the spatial distribution, velocity, and physical properties of HVCs, offering insights into their origins and relationships to the host galaxies. The study of HVCs also benefits from simulations and theoretical models that replicate the interactions and evolution of gas in galactic halos. Overall, the presence of HVCs highlights the dynamic and ongoing processes that shape galaxies. Their study provides important clues about the mechanisms of gas recycling, accretion, and interaction in the universe, deepening our understanding of galaxy formation and evolution over cosmic time. Through continued observations and research, astronomers aim to unravel the complex origins and roles of these enigmatic high-velocity clouds in galactic halos. Picture a galaxy not as a solitary island of stars, but as a bustling city with tributaries of stars flowing in from all directions, illustrations of its rich past. Stellar streams are these tributaries, sprawling ghostly trails of stars stretched out across the sky. Imagine a smaller galaxy, perhaps a dwarf galaxy, getting too close to a larger galaxy like the Milky Way. The immense gravitational forces of the larger galaxy begin to pull on the stars of the dwarf galaxy, stretching it like cosmic taffy. This process, known as tidal stripping, effectively peels away the stars and gases from the dwarf galaxy, creating a stream of stars that orbit the larger galaxy's halo. It's a cosmic dance of attract and tear, repeated over billions of years. What's captivating is that these streams act like cosmic fossils. They retain the memory of the smaller galaxy's past motions and compositions, even after their progenitor galaxy has dissolved. Scientists study stellar streams to uncover the dark matter distribution around galaxies, as the pattern of these streams can indicate where invisible dark matter is most densely packed. Think of it as reading ancient imprints on a cosmic map. Utilizing measurements from telescopes like the Gaia spacecraft, researchers can trace these faint structures and decode the gravitational forces at play. With numbers like 100,000 stars becoming part of a stellar stream over the course of 1 billion years, these celestial formations not only tell tales of galactic cannibalism, but also reveal hidden secrets of the universe's architecture. Dark matter is an enigma wrapped in the cloak of the universe. Scientists have yet to decipher its precise composition, but several intriguing hypotheses guide their investigations. Unlike ordinary matter, which is composed of protons, neutrons, and electrons, dark matter does not interact with electromagnetic forces, meaning it doesn't emit, absorb, or reflect light. This makes it invisible, detectable only through the gravitational effect it exerts on visible matter, the bending of light from distant stars, and the overall structure of galaxies. One of the leading candidates for dark matter's composition is weakly interacting massive particles, or WIMPs. These hypothetical particles are thought to be heavy, roughly 100 times the mass of a proton, yet interact only through the weak nuclear force and gravity, making them elusive and difficult to detect with current instruments. Another fascinating candidate is axions, extremely light particles that, if they exist, could form a Bose-Einstein condensate, a state of matter where particles collectively behave as a single quantum entity. Scientists are also exploring the possibility of sterile neutrinos, a type of neutrino that does not interact via the weak force like ordinary neutrinos. Despite these theories, what dark matter actually consists of remains one of the biggest mysteries in cosmology. An invisible hand shaping the cosmos, inferred from the movements and formations that visible matter makes in response to its unseen touch. Dark matter's interaction with ordinary matter is a subtle, almost ghostly dance, one where the partners rarely touch, but influence each other through an invisible force. Unlike the particles that make up stars, planets, and even ourselves, dark matter doesn't interact with ordinary matter through electromagnetic forces. This means it doesn't emit, absorb, or reflect light, rendering it invisible to telescopes that detect visible infrared or even X-ray light. The primary way dark matter interacts with ordinary matter is through the force of gravity. Imagine an intricate ballet where dark matter forms the stage, and ordinary matter moves in response to its gravitational pull. This gravitational interaction is so significant that it shapes the formation of galaxies and clusters of galaxies. Observations show that galaxies rotate with such speed that they should fly apart if only ordinary matter were influencing them. However, the presence of dark matter provides the additional gravitational force needed to hold these galaxies together. Another way we detect this interaction is through gravitational lensing, a phenomenon where the massive gravitational field of dark matter bends light from distant stars and galaxies, distorting their images from our perspective on Earth. In addition to these large-scale influences, scientists are designing sophisticated experiments to detect potential particle interactions between dark matter and ordinary matter, albeit weak ones. Deep underground laboratories house detectors aimed at capturing rare instances where a dark matter particle might collide with a nucleus of ordinary matter, imparting a minuscule yet detectable amount of energy. Without interacting via electromagnetic forces, dark matter's gravitational handshake with the universe provides the scaffolding upon which galaxies are built and thrive, teasing scientists with clues about its fundamental nature. Directly detecting dark matter is akin to trying to see the wind. We notice its presence not by observing the wind itself, but by the way it makes leaves rustle and trees sway. Dark matter eludes direct detection because it does not interact with light, which is the primary means we use to see and measure the universe. While ordinary matter engages in a constant interplay of electromagnetic forces, emitting and absorbing light, bouncing off other particles, dark matter remains indifferent to such interactions. This invisibility cloaks it from our most powerful telescopes and detectors designed to capture particles of light, such as photons. The quest to catch a glimpse of dark matter involves several ingenious approaches. One method aims to detect the rare, faint whispers of dark matter particles interacting with atomic nuclei. Experiments like those conducted in the deep underground laboratories of the Large Underground Xenon Detector, or its successor, Luke Zeppelin, involve vast tanks filled with noble gases like xenon. These tanks are buried deep underground to shield them from cosmic rays and other background noise. The concept is that, occasionally, a dark matter particle might jostle an atomic nucleus in the xenon tank, causing a tiny flash of light or a minuscule burst of energy that highly sensitive detectors could capture. Another promising, albeit indirect method involves searching for evidence of dark matter annihilation or decay. In some theories, when two dark matter particles collide, they may annihilate and produce detectable particles such as gamma rays. Instruments like the Fermi Gamma Ray Space Telescope are tuned to spot such high-energy signals originating from regions with expected high concentrations of dark matter, like the center of our galaxy. Despite these sophisticated efforts, the elusive nature of dark matter makes it a profound puzzle. Each attempt to detect it directly may feel like searching for a needle in a haystack where the needle doesn't reflect light. But every effort brings us a step closer to unraveling one of the universe's deepest secrets. The story of galaxy formation cannot be fully told without the shadowy influence of dark matter. Picture dark matter as an invisible scaffolding or web that stretches across the universe, setting the stage for galaxies to take form and evolve. This invisible network, often called the cosmic web, consists of vast filaments of dark matter that weave through the cosmos, intersecting at nodes where galaxy clusters tend to form. In the early universe, shortly after the Big Bang, the distribution of both dark matter and ordinary matter was relatively uniform. However, even slight fluctuations in this distribution were amplified over time by gravity. Dark matter, being unaffected by radiation pressure and interacting only through gravity, began to clump together into dense regions. These dark matter clumps, or halos, provided the gravitational wells necessary to attract and gather ordinary matter, hydrogen and helium gases. As these gases fell into the potential wells created by dark matter, they began to cool and condense, eventually leading to the birth of the first stars and galaxies. Without dark matter, the gravitational pull exerted solely by ordinary matter would have been insufficient to form the structures we see today within the universe's age. This makes dark matter the unseen architect of galaxies, lending the gravitational blueprint around which ordinary matter could coalesce and complex structures could emerge. For instance, simulations of the universe's evolution that include dark matter accurately reproduce the filamentary structure of the cosmic web and the distribution of galaxies, while those excluding dark matter fail to match observed reality. Observations support this intertwined relationship. For instance, the rotation curves of galaxies, plots of rotational speed versus distance from the galactic center, reveal that stars on the periphery rotate much faster than can be accounted for by the visible matter alone. This discrepancy suggests the presence of a massive halo of dark matter enveloping each galaxy, exerting the necessary gravitational force to hold the stars within. Thus, while dark matter remains elusive and intangible, its imprint is unmistakable in the cosmic tapestry of galaxies and the very structure of the universe itself. Dark energy is the enigmatic force driving the universe's accelerating expansion, a phenomenon that has left scientists both intrigued and baffled. Imagine the universe as a balloon with galaxies and cosmic structures represented by dots on its surface. As you blow more air into the balloon, the dots move away from one another, illustrating how space itself stretches. For much of cosmic history, gravity, which pulls matter together, was thought to be the dominant force governing the expansion. However, observations in the late 1990s from distant supernova revealed something astonishing. The expansion of the universe isn't just continuing, it's speeding up. This unexpected acceleration suggests the presence of a repulsive force counteracting gravity, known as dark energy. While dark matter clumps together due to gravity, dark energy seems to have the opposite effect. It pushes space apart. One prevalent theory posits that dark energy is related to the cosmological constant, an idea originally put forth by Einstein. The cosmological constant represents a uniform energy density that permeates space, providing a steady additive force that causes the universe to expand faster over time. Another compelling theory suggests that dark energy might be a new dynamic field dubbed quintessence, which evolves and changes over time, differing somewhat from the constant nature of the cosmological constant. Numerically, around 70% of the universe's energy density is attributed to dark energy. Its influence becomes more pronounced as the universe expands because, unlike matter which becomes more diluted, dark energy's density remains constant or nearly constant. This constant energy density means that as more space is created through expansion, more dark energy comes into play, further accelerating the expansion. Cosmologists and physicists employ methods like observing the cosmic microwave background, the faint afterglow of the Big Bang, alongside large-scale galaxy surveys, to understand dark energy's effects better. These methods help map the expansion history of the universe, offering key insights into how dark energy operates over cosmic time. The result is a profound shift in our understanding of the universe, an accelerating cosmos driven by a mysterious force that challenges the very fabric of space-time. The nature of dark energy, whether it remains constant or changes over time, is a central question in cosmology that continues to fuel deep scientific inquiry. There are two primary schools of thought on this matter, each with fascinating implications for the fate and structure of the universe. The first and currently most widely accepted hypothesis is the cosmological constant, often denoted by the Greek letter lambda. This idea, originally introduced by Einstein, suggests that dark energy is a constant energy density filling space homogeneously. In this scenario, as the universe expands, the amount of dark energy per unit volume remains the same. This constant energy density acts like a repulsive force, continually accelerating the expansion of the universe. The constancy of dark energy in this model simplifies calculations and aligns well with many observational data, such as the cosmic microwave background radiation and the distribution of galaxies. However, the alternative hypothesis is equally intriguing and posits that dark energy may not be constant. This dynamic dark energy model is often referred to as quintessence. In quintessence theories, dark energy is represented as a field that evolves over time, changing its density and properties as the universe expands. Unlike the cosmological constant, which is unchanging, quintessence could lead to a variety of possible fates for the universe. For instance, if the energy density of quintessence increases over time, it could lead to a big rip, where galaxies, stars, and even atoms are eventually torn apart. Conversely, if it decreases, the expansion could slow, halting, or even reversing into a big crunch. To determine which model reflects reality, cosmologists use a variety of observational tools. Measurements of distant supernovae, cosmic microwave background fluctuations, and large-scale structure formations help scientists track the universe's expansion history and infer the properties of dark energy. Future missions, such as the James Webb Space Telescope and the Euclid mission, are expected to provide even more precise data, potentially distinguishing between a constant cosmological constant and a dynamic field like quintessence. Hence, the question of dark energy's constancy is not just academic, it touches upon the ultimate destiny of the cosmos and our understanding of fundamental physics, making it one of the most compelling mysteries in modern science. Modified gravity theories propose a revision to our understanding of gravity to explain the phenomena attributed to dark matter and dark energy. These theories challenge the standard model by suggesting that the equations governing gravity might need tweaking when applied to cosmological scales. Let's start with dark matter. Traditional models, such as general relativity, predict gravitational effects that don't match up with observations unless an unseen extra mass, dark matter, is invoked. Modified Newtonian dynamics, or MOND, is one such theory. Proposed by physicist Mordechai Milgram in the early 1980s, MOND suggests that at very low accelerations, typical in the outer regions of galaxies, the laws of gravity differ from Newton's laws. In MOND, the gravitational pull decreases more slowly than expected, thereby explaining the faster rotation speeds of outer stars in galaxies without requiring dark matter. However, while MOND can successfully describe certain galactic behaviors, it struggles to explain the large-scale structure of the cosmos and galaxy clusters, where dark matter seems indispensable. On the other hand, general relativity's extensions like tensor vector scalar gravity, TVS, and FR gravity aim to offer a more comprehensive approach. These theories modify Einstein's equations to include additional fields or geometric terms, potentially accounting for both dark matter and cosmological observations without invoking unseen particles directly. While promising, these theories also face significant challenges, requiring intricate fine-tuning to align with observations and not always delivering predictive power across different cosmic scales. When it comes to dark energy, modified gravity theories suggest that adjustments to our understanding of spacetime's geometry might eliminate the need for a mysterious energy component driving the universe's accelerated expansion. One popular framework is the Brans-Dicker theory, where gravity's strength can vary with time and space due to an additional scalar field. Alternatively, some FR gravity models modify the Einstein-Hilbert action in general relativity, adding higher-order terms of the Ricci curvature scalar, which can induce cosmic acceleration without dark energy. One compelling candidate here is the theory of massive gravity, which posits that the graviton, the hypothetical particle mediating the force of gravity, has a small but non-zero mass. This mass can introduce a gravitational force that mimics the effects of dark energy, pushing the universe to accelerate its expansion. Yet these theories face hurdles. They must reconcile with well-established tests of general relativity within our solar system while also accurately describing phenomena on cosmological scales. Experiments and observations, such as gravitational wave detections by LIGO and Virgo, and the detailed mapping of cosmic microwave background fluctuations, continually test and refine these models. In effect, modified gravity theories provide a bold and fascinating route, aiming to unify the cosmic conundrums of dark matter and dark energy within a revised framework of gravitational theory. The ongoing advancements in astronomical observation and experimental physics will play a crucial role in testing these theories, potentially redefining our understanding of the universe's most elusive components. Galaxy clusters, the largest gravitationally bound structures in the universe, serve as compelling laboratories for uncovering the mysteries of dark matter. These colossal assemblies of galaxies, hot gas, and dark matter provide multiple lines of evidence that dark matter is a crucial ingredient in the cosmic recipe. Firstly, galaxy clusters exhibit gravitational effects that far exceed what can be explained by visible matter alone. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster and discovered that the velocities of individual galaxies within the cluster were far too high to be held together merely by the gravitational pull of the visible matter. He proposed the existence of missing mass, which we now refer to as dark matter, to account for this discrepancy. This gravitational anomaly signifies that an unseen mass must be present to generate the necessary gravitational force to keep the cluster intact. Another compelling piece of evidence comes from observations of gravitational lensing. According to general relativity, massive objects can warp the fabric of spacetime, bending the path of light from background objects. Galaxy clusters, with their immense mass, act as natural gravitational lenses, distorting and magnifying the light from galaxies lying behind them. By analyzing these distortions, astronomers can map the mass distribution within the cluster. These maps invariably show that the gravitational lensing effect is far stronger than can be accounted for by visible matter alone, implying the presence of a significant amount of dark matter. Additionally, the hot gas that permeates galaxy clusters offers another clue. This gas is so hot, millions of degrees Kelvin, that it emits X-rays, which can be detected by space telescopes like Chandra. The pressure of this gas should cause it to escape the cluster, but observations show that it remains tightly bound within these clusters. This retention of hot gas suggests the presence of a massive, unseen component, again pointing to dark matter, that provides the extra gravitational pull needed to contain this high-energy gas. The Bullet Cluster, 1E065756, provides one of the most striking confirmations of dark matter's existence. This system is the result of a high-speed collision between two galaxy clusters. Observations from the Chandra X-ray Observatory show the hot gas from the two clusters colliding and slowing down, while gravitational lensing maps reveal that the bulk of the total mass, inferred to be dark matter, has passed through the collision unaffected, effectively separating from the hot gas. This separation demonstrates that the dark component is not interacting electromagnetically, reinforcing the notion that it behaves very differently from ordinary matter. In sum, galaxy clusters serve as colossal cosmic scales, repeatedly tipping in favor of dark matter. Their gravitational behavior, the influence on light through lensing, and the dynamics of their hot gas all intertwine to weave a compelling narrative, underscoring the critical role dark matter plays in shaping the universe. Dark matter plays an instrumental role in sculpting the cosmic web, the vast and intricate structure that forms the backbone of our universe. This sprawling network of filaments and voids stretches across the cosmos, connecting galaxies and galaxy clusters like beads on a string. To understand how dark matter shapes this grand architecture, imagine that the early universe was a nearly uniform sea of particles, both dark and ordinary, with tiny fluctuations in density. These minuscule density variations, amplified by gravity over billions of years, allowed dark matter to start clumping together into small regions of higher density, known as dark matter halos. Given that dark matter constitutes about 85% of the total matter in the universe, its gravitational pull significantly outweighed that of ordinary matter. These initial dark matter clumps served as the gravitational seeds, pulling in nearby gas and dust to form stars and galaxies. The massive dark matter filaments stretched across space, creating the scaffolding for what would become the cosmic web. As the universe continued to expand, these dark matter halos merged and interacted, forming larger and more complex structures. Supercomputers have accurately simulated this evolution, showing how dark matter's gravitational influence orchestrates the growth of the cosmic web. In these simulations, you can observe dark matter drawing strands of ordinary matter along its gravitational highways, funneling gas into dense nodes where galaxy clusters thrive. These nodes are interconnected by vast filaments of dark matter, which guide the motion and formation of galaxies along their paths. Moreover, dark matter's gravitational influence ensures that the cosmic web maintains its intricate yet robust structure. Without dark matter, ordinary matter would not have had enough gravitational clout to form the vast, interconnected structures observed in the universe today. Essentially, dark matter acts as the universe's skeletal framework, with ordinary matter serving as the flesh, creating the luminous galaxies and stars we observe. Observations of the large-scale structure of the universe provide empirical evidence supporting this role of dark matter. The cosmic microwave background radiation, the afterglow of the Big Bang, offers a snapshot of the early universe's density fluctuations. These fluctuations have grown into the cosmic web structures we see today, and models incorporating dark matter align closely with observed galaxy distributions and their large-scale clustering. In conclusion, dark matter is not merely a supporting actor, but rather the principal architect of the cosmic web. It shapes the universe's large-scale structure, dictating the formation and distribution of galaxies, and embedding itself into the very fabric of cosmic evolution. The nature of dark energy is a pivotal factor in determining the ultimate fate of the universe, acting as the invisible hand that governs cosmic expansion. Dark energy, which constitutes approximately 70% of the universe's energy density, has already been observed to drive the accelerated expansion of the cosmos. The characteristics of this mysterious force, whether it remains constant or changes over time, will decisively influence how the universe evolves and ends. If dark energy is indeed a cosmological constant, as proposed in the lambda cold dark matter model, its energy density would remain uniform over time. In this scenario, the universe will continue to expand at an accelerating rate indefinitely. Galaxies would drift further apart, stars would eventually exhaust their nuclear fuel, and over an incredibly long timescale, the universe would evolve into a cold, dark, and increasingly empty expanse. This scenario is often termed the Big Freeze or heat death, where the universe approaches thermodynamic equilibrium, with progressively fewer energy transformations occurring over time, leading to a state of maximum entropy. However, if dark energy is a dynamic field, such as quintessence, its properties could change over time. This fluid-like dark energy might either increase or decrease in strength. Should the dark energy density increase, it could lead to a scenario known as the Big Rip. In this wild future, the accelerating expansion could become so extreme that it eventually overcomes all other forces. Galaxies, stars, planets, and eventually atomic structures themselves would be torn apart by the relentless expansion. The timeline for such an event depends on the rate at which dark energy's repulsive force escalates, but it could happen within a conceivable billions of years time frame. Alternatively, if the dark energy density decreases or reverses into a repulsive then attractive form, we might face a big crunch. Here, the expansion of the universe could slow down, halt, and then reverse, causing the universe to collapse back into a singularity-like state. This cyclical model suggests that the universe could potentially bounce back, leading to another Big Bang-like event, perpetuating a possibly infinite series of cosmic rebirths and destructions. Dark energy's nuances are still largely unknown, so cosmologists employ various observational tools to decode its properties. Surveys of distant supernovae, analyses of the cosmic microwave background, and detailed mappings of large-scale structures contribute to our understanding. Future missions, such as the Euclid Space Telescope and the James Webb Space Telescope, are anticipated to provide more precise measurements of dark energy and its effects over cosmic distances and timescales. In sum, the true nature of dark energy is the linchpin in our cosmic fate. Whether it leads to an ever-expanding freeze, a violent rip, or a cataclysmic crunch, dark energy's characteristics will chart the course of the universe's destiny, making it one of the most profound questions in contemporary cosmology. Inside a black hole's event horizon, we venture into one of the most extreme and mysterious environments in the universe, where the laws of physics as we understand them are stretched to their limits. The event horizon is the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. Once crossed, the path forward leads inexorably to the singularity, the core of the black hole where all its mass is thought to be concentrated. As an object approaches the event horizon, it experiences increasingly intense gravitational forces. One of the most dramatic effects is spaghettification, or the tidal stretching effect. Near a black hole, the gravitational force you feel is intensely stronger on the side closer to the singularity than on the side farther away. For example, if you were falling feet first into a black hole, the gravitational pull at your feet would be immensely stronger than at your head, causing your body to stretch into a long, thin shape. Once past the event horizon, the nature of space-time changes radically. According to general relativity, the fabric of space-time inside the event horizon is so distorted that all possible paths within it lead closer to the singularity. The concept of time and space as we know them becomes warped beyond recognition. To an external observer, it would appear as though time for the infalling object slows down dramatically as it approaches the event horizon, eventually freezing as it reaches the boundary. However, from the perspective of the object itself, it would continue to fall inward, wholly unaware of any bizarre time dilation effects. The singularity at the center of the black hole represents a point where densities become infinite and the conventional descriptions of space and time break down. Physicists struggle to understand what happens in such extreme conditions because, at this point, the known laws of physics, including general relativity and quantum mechanics, lose their predictive power. Current theories suggest that all the information about the infalling matter is compressed into an infinitely small space, a notion that brings forth the so-called information paradox. The paradox questions how information about the matter that falls into a black hole can reconcile with the principles of quantum mechanics if it seemingly disappears forever. The extreme conditions comprising both immense gravity and quantum effects within a black hole imply that a unified theory of quantum gravity is needed to fully grasp the dynamics at play. Various hypotheses, such as string theory and loop quantum gravity, are being explored to understand what happens beyond the event horizon. Still, much remains speculative. Crossing a black hole's event horizon is a one-way journey into the unknown, plunging into a realm where time and space merge, matter is annihilated into singularity, and the known laws of physics may no longer apply. The mysteries inside the event horizon continue to push the boundaries of our understanding, beckoning to the day when a new, comprehensive theory might unlock their secrets. Supermassive black holes, residing at the centers of most, if not all, large galaxies, exert profound influence on their host galaxies' evolution, shaping their structure, dynamics, and star formation activities. These cosmic giants, containing masses ranging from millions to billions of times that of our Sun, act as both creative and destructive forces in galactic ecosystems. One of the most direct ways supermassive black holes affect their galaxies is through their active galactic nucleus phase. During this phase, the black hole accretes vast amounts of gas and dust from its surroundings, funneling this material into a rapidly spinning accretion disk. The infalling matter heats up immensely as it spirals inward, emitting tremendous amounts of energy in the form of light, X-rays, and even relativistic jets. This phenomenon creates some of the brightest objects in the universe, such as quasars. The energy emitted by an AGN can have sweeping consequences for the host galaxy. High-energy radiation and powerful jets can heat and blow away surrounding gas, quenching star formation by depleting the material that would otherwise cool and condense into new stars. This process, known as feedback, can regulate the growth of the galaxy, maintaining a balance between star formation and gas inflow. Observations across a range of wavelengths, from radio to X-ray, illustrate these interactions vividly. For instance, the radio jets of galaxies like Cygnus A can extend hundreds of thousands of light-years, depositing energy far beyond the immediate vicinity of the black hole into the interstellar and even intergalactic medium. These jets can trigger or suppress star formation in neighboring regions by compressing gas clouds or blasting them apart. Supermassive black holes also play a crucial role in the morphologies and dynamics of their galaxies. Studies have shown a remarkable correlation between the mass of the central black hole and the properties of the host galaxy's bulge, particularly the velocity dispersion of stars in it, a relationship known as the M-sigma relation. This tight correlation hints at a co-evolution of black holes and their galaxies, suggesting that the growth of a black hole is somehow intimately linked to the development of its host galaxy. Furthermore, in galaxy mergers, events that are pivotal in galactic evolution, supermassive black holes are believed to form binary systems, orbiting each other before eventually merging themselves. Such cataclysmic events are not just dramatic. They release gravitational waves, ripples in space-time predicted by Einstein and observed by detectors like LIGO and Virgo. The merger of these supermassive objects likely leads to significant outflows of gas and energy, influencing star formation rates and redistributing mass within the galactic hosts. Supermassive black holes are far more than passive residents of galaxy centers. They are dynamic entities with the ability to shape their galactic neighborhoods profoundly. Through mechanisms like AGN feedback, jet emissions, and their significant gravitational pull, they regulate star formation, influence galaxy morphology, and contribute to the overall evolutionary narratives of galaxies, playing a role of a cosmic architect whose impacts are felt over billions of years. Quasi-periodic oscillations, QPOs, in black hole emissions are fascinating phenomena observed in the light curves of X-ray binaries, where a stellar mass black hole accretes matter from a companion star. These oscillations, with regular yet variable periods, offer crucial insights into the complex dynamics around black holes. Several mechanisms have been proposed to explain QPOs, each relating to different aspects of the accretion process, the inner disk dynamics, and relativistic effects near the black hole. One leading hypothesis is that QPOs arise from the inner regions of the accretion disk, where gas spirals inward before crossing the event horizon. These inner disk regions are subject to intense gravitational and magnetic forces, which can create various types of periodic behavior. For instance, the lens-Thirring precession, a relativistic effect predicted by general relativity, might play a significant role. As matter orbits the black hole, it experiences frame dragging due to the black hole's spin, causing the orbit to precess. This precessional motion could modulate the emitted X-ray signals, leading to the observed quasi-periodic oscillations. Another intriguing explanation involves the concept of resonant oscillations within the accretion disk. Just as musical instruments can resonate at specific frequencies, parts of the disk might hit resonant frequencies, leading to coherent oscillatory modes. These oscillations could be linked to the disk's inner edge, particularly where the gas interacts most dynamically with the black hole's gravitational well. Magnetic fields threading the disk can also play a part, as magnetohydrodynamic (MHD) waves could induce periodic modulations in the emitted X-rays. Additionally, QPOs may stem from instabilities in the accretion flow itself. The material being accreted can vary in density and temperature, creating regions of fluctuating emission. These density waves or thermal instabilities could travel through the disk, periodically enhancing or dimming the X-ray output as they pass through regions where the energy release is most intensive. This results in a pattern that, while regular, exhibits slight variations, hence the term quasi-periodic. Observational data from X-ray telescopes like NASA's Rossi X-ray Timing Explorer, RXTE, and ESA's XMM Newton have provided rich datasets for studying QPOs. These observations show that QPOs often come in two varieties: low-frequency QPOs, ranging from fractions of a hertz to a few hertz, and high-frequency QPOs, up to several hundred hertz. The simultaneous presence and interaction of these different oscillatory modes further complicate the picture, indicating that multiple mechanisms might be at play, potentially contributing to a broader understanding when combined. Ultimately, while the precise cause of QPOs remains an active area of research, the interplay of orbital mechanics, relativistic effects, magnetic fields, and instabilities within the accretion process presents a multifaceted landscape. Each new observation helps to piece together the complex puzzle, offering deeper insights into the environments around black holes and the extreme physics governing these enigmatic regions of space-time. Binary black hole systems provide an extraordinary window into the dynamics of gravitational interaction and the intricate dance of cosmic titans. The evolution and eventual merger of such binary systems proceed through several distinct phases, each characterized by complex processes governed by the laws of general relativity and astrophysics. Initially, binary black hole systems form through various channels. One possible pathway is the dynamical interaction within dense stellar environments like globular clusters or galactic cores. In these crowded arenas, encounters between stars and compact remnants such as black holes can lead to the formation of close pairs. Alternatively, binary black holes might arise from the evolution of massive binary star systems. In this scenario, each star in a binary pair may undergo a supernova, leaving behind two black holes that remain gravitationally bound. Once formed, the binary black holes embark on an intricate gravitational dance, spiraling closer together as they lose energy primarily through the emission of gravitational waves. This process can be described in several phases. 1. Asterisk asterisk. In spiral phase asterisk asterisk. During this initial phase, the two black holes orbit each other at a relatively large separation. As they emit gravitational waves, which are ripples in the fabric of space-time, they lose energy and angular momentum. The loss is minuscule at first, causing the black holes to spiral inward at a slow pace. This phase can last millions or even billions of years, depending on the initial separation and masses of the black holes. 2. Asterisk asterisk merger. Phase asterisk asterisk. As the black holes draw closer, the gravitational wave emission intensifies, causing a rapid inward spiral. Eventually, they reach a critical separation where the inspiral accelerates dramatically, bringing them into a vortex of increasingly powerful gravitational wave production. This final stage lasts only seconds. The black holes merge to form a single, more massive black hole. The process is accompanied by a burst of gravitational waves so intense that detectors like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo can observe them even from hundreds of millions of light-years away. These observations not only confirm the existence of binary black holes, but also validate general relativity's predictions in the strong field regime. 3. **** ring-down phase ***. After the merger, the newly formed black hole is initially in a highly excited state and not perfectly spherical. It undergoes a phase called ring-down, where it emits gravitational waves to settle into a stable, spinning, nearly spherical shape. The ring-down phase acts like a cosmic bell, ringing out the residual energy in the form of gravitational waves until the new black hole reaches equilibrium. The gravitational waves emitted during these phases carry distinct signatures that allow scientists to extract valuable information about the black hole's masses, spins, and even the nature of the merger process itself. For instance, the gravitational wave event GW150914, detected by LIGO in 2015, provided the first direct observation of a binary black hole merger, ushering in a new era of gravitational wave astronomy. Binary black hole systems can also experience additional astrophysical processes. For instance, surrounding matter and interactions with third bodies, such as another star or black hole, can influence the binary's evolution. In some cases, the eccentricity of the orbit may increase or decrease due to these interactions, affecting the merger timeline. From formation through dynamic interaction or stellar evolution to the final cataclysmic merger, binary black hole systems showcase the universe's extremes. They offer a unique glimpse into the complex interplay of gravitational forces and the behavior of matter in the most intense environments, enhancing our understanding of fundamental physics and the life cycles of black holes. The force behind the powerful jets emanating from active galactic nuclei begins with a supermassive black hole, typically millions to billions of times the mass of our Sun, residing at the galaxy's core. This behemoth of gravity gathers a swirling disk of gas, dust, and stellar debris, known as the accretion disk, around its event horizon. Within this disk, particles move at extraordinary speeds, and extreme frictional forces heat them to temperatures of millions of degrees. Magnetic fields generated by the rotating disk become twisted and coiled, much like taut springs storing immense energy. The mechanisms that drive these jets are incredibly complex and only partially understood, but it's clear that the magnetic fields play a crucial role. They can funnel particles from the accretion disk along the black hole's spin axis, effectively accelerating them to nearly the speed of light, forming collimated jets that shoot out perpendicular to the disk. These jets can stretch across thousands to even millions of light-years, shining brilliantly in radio, optical, and X-ray wavelengths. The incredible energy of these relativistic jets can impact entire galactic ecosystems, influencing star formation and the distribution of gas and dust far beyond the galaxy's center, making these cosmic geysers both fascinating and significant to our understanding of the universe. Intermediate mass black holes, generally defined as having masses between 100 and 100,000 times that of our Sun, present a compelling puzzle in astrophysics. Their formation scenarios bridge the gap between the stellar mass black holes, which are remnants of massive stars, and the supermassive black holes found at galactic centers. One prominent theory suggests that they could form through repeated mergers of smaller black holes and neutron stars. Imagine a densely packed star cluster where interactions are frequent. The gravitational dance of its members can lead some to collide and merge, gradually building up mass over time. Another intriguing possibility is that they arise from the collapse of massive primordial gas clouds in the early universe. These gas clouds, significantly free of heavier elements, could avoid the usual fragmentation process that leads to star formation and instead collapse directly into black holes. Additionally, some scientists propose that intermediate mass black holes could form within young, massive star clusters. Here, runaway collisions and mergers of massive stars before they end their lives could produce a very massive star, which then directly collapses into an intermediate mass black hole. Evidence for these black holes remains sparse, but recent detections of gravitational waves and observations of ultra-luminous X-ray sources indicate we might be closing in on these elusive cosmic heavyweights. As a black hole approaches its final stages of evaporation, it becomes a cosmic spectacle of extreme physics. This fascinating process is governed by Hawking radiation, a theoretical prediction made by physicist Stephen Hawking in the 1970s. According to this theory, black holes are not entirely black, but instead emit faint radiation due to quantum effects near their event horizons. Over incredibly long timescales, much longer than the current age of the universe for most black holes. This radiation causes the black hole to lose mass. As the black hole's mass decreases, its temperature rises and it emits radiation more intensely. During the final moments, this process accelerates rapidly. When a black hole dwindles to a minuscule scale, it could release an enormous burst of energy, potentially equivalent to the explosion of millions of hydrogen bombs. This termination flash would signify the black hole's ultimate demise, dispersing its remaining mass energy into space and leaving nothing but an empty void where one of the universe's most enigmatic objects once resided. This dramatic end to a black hole's existence continues to intrigue physicists, challenging our understanding of quantum mechanics, general relativity, and the fundamental nature of space and time. Primordial black holes and stellar black holes represent two fascinating yet distinct astrophysical phenomena. Primordial black holes are thought to have formed in the high-energy environments of the early universe, mere moments after the Big Bang. These black holes might have originated from density fluctuations in the universe's primordial soup, areas where the concentration of mass was sufficient to collapse directly into black holes without needing the formation and death of stars. The potential masses of these primordial black holes can span a wide range, from fraction of a gram to many times the mass of the Sun. Stellar black holes, on the other hand, are born from the life cycles of massive stars. They form when a star with more than about 8 times the mass of the Sun exhausts its nuclear fuel. The core collapses under its own gravity, leading to a supernova explosion that blows off the outer layers, while the core itself continues to compress into a black hole, often with masses between a few and a few dozen times that of the Sun. These remnants are generally found within galaxies, sometimes as part of binary systems where they interact with companion stars, leading to X-ray emissions that we can observe. While stellar black holes are relatively well documented through various observational techniques like X-ray astronomy and gravitational wave detections, primordial black holes remain a more enigmatic possibility with no definitive direct evidence yet. However, they are of great interest because if they exist, they could contribute to unexplained phenomena such as dark matter or even the seeds for the formation of the supermassive black holes at the centers of galaxies. Frame dragging is a fascinating consequence of the theory of general relativity, first introduced by Albert Einstein. Around rotating black holes, such as those described by the Kerr solution to Einstein's equations, this effect becomes especially pronounced. When a black hole spins, it doesn't merely pull in material through its immense gravitational field, it also drags the very fabric of space-time along with it. This phenomenon, often referred to as the lens-Thirring effect, means that any object in the vicinity of the rotating black hole will be influenced not just by gravity pulling it inward, but also by a twisting motion of space-time itself. The degree of this space-time twisting depends on the black hole's mass and the speed at which it rotates. Near the event horizon, this effect is so strong that it can significantly alter the paths of nearby particles and light, effectively forcing them to orbit in the direction of the black hole's spin. For example, the space station around a rotating black hole would rotate because space-time itself is moving. Frame dragging has practical implications for understanding the dynamics around black holes and has been observed around Earth using the Gravity Probe B experiment, although the effects are much subtler given Earth's comparatively weak gravitational field and slow rotation rate. The extreme conditions near a rotating black hole make frame dragging highly significant, affecting the orbits of matter in accretion disks and the trajectories of relativistic jets. This not only influences how black holes grow and interact with their surroundings, but also provides a testing ground for theories of gravity. Understanding frame dragging helps astronomers decipher the intricate dance of matter and energy near some of the most exotic objects in our universe. Gravitational lensing is a mesmerizing phenomenon where massive objects like black holes bend the fabric of spacetime so intensely that they can deflect the paths of light rays passing nearby. This effect is a direct consequence of Einstein's theory of general relativity, which tells us that mass curves spacetime, and thus light, which always travels along the straightest possible path in curved space, gets bent around these massive objects. Picture spacetime as a stretchy, flexible sheet. A black hole is like a heavy ball placed on that sheet, creating a deep well. When light passes close to this well, its path gets bent, much like a car navigating a curvy road. For black holes, which have extraordinarily intense gravitational fields, this bending can be extreme. Light from a background star or galaxy that passes near a black hole can be curved so sharply that it can produce multiple images of the same astronomical object. In some cases, the light can even loop around the black hole multiple times, creating a phenomenon known as an Einstein ring, where the background object appears as a ring of light encircling the black hole. The degree of this lensing effect depends on the black hole's mass and the relative alignment between the black hole, the light source, and the observer. Gravitational lensing around black holes doesn't just create dramatic and beautiful images, it also serves as a crucial tool in cosmology and astrophysics. By studying the distorted light, scientists can infer properties about the black hole, such as its mass and possibly its spin. Moreover, lensing events allow astronomers to peer farther into the universe, magnifying distant galaxies and helping us understand the distribution of dark matter. This impressive manipulation of light underscores the profound ways in which black holes interact with their cosmic surroundings, revealing the invisible architecture of the universe itself. Fast radio bursts, FRBs, are among the most enigmatic phenomena in the cosmos, characterized by incredibly short but extremely powerful bursts of radio waves, lasting only a few milliseconds. Despite their brief existence, these bursts can release as much energy in a single millisecond as the sun does in nearly a century. The exact cause of FRBs remains an area of active research and speculation, but several compelling theories propose fascinating origins. One leading hypothesis suggests that FRBs may originate from highly magnetized rotating neutron stars known as magnetars. Magnetars are rare types of neutron stars with magnetic fields thousands of times stronger than typical neutron stars. These powerful magnetic fields can produce intense bursts of energy through mechanisms such as magnetic reconnection or starquakes, sudden shifts in the star's crust. The energy released in these processes can generate the rapid, intense radio waves detected as FRBs. Another intriguing possibility is that FRBs result from catastrophic events in binary star systems. For instance, the merging of two neutron stars or a neutron star colliding with a black hole could produce shockwaves and magnetic interactions powerful enough to generate these radio bursts. Some theories also speculate that the presence of exotic objects like primordial black holes or even advanced extraterrestrial technology could be responsible, although these ideas remain highly speculative. What makes FRBs even more mysterious is that some have been observed repeating but with irregular intervals, while others seem to occur just once. This diversity implies that there might be multiple origins or mechanisms producing FRBs, adding layers of complexity to unraveling their secrets. Continued observations with sophisticated radio telescopes, such as the Chime radio telescope in Canada and the Parkes Observatory in Australia, aim to capture more FRBs and their characteristics, bringing us closer to solving this cosmic mystery. Magnetars are a mesmerizing subset of neutron stars that possess magnetic fields of unparalleled strength, often 1,000 times greater than those of typical neutron stars and billions of times stronger than any magnetic field produced on Earth. These colossal magnetic fields are thought to arise from the intense and violent conditions prevailing during the formation of the neutron star itself. When a massive star, over 8 times the mass of our Sun, exhausts its nuclear fuel, it undergoes a supernova explosion, leaving behind a dense core comprised almost entirely of neutrons. The prevailing theory explains that magnetars may form when this core's rotation combines with powerful convection currents and fluid dynamics in the newborn neutron star. If the core retains a rapid spin rate, on the order of milliseconds, it can amplify any pre-existing magnetic fields through a process known as the dynamo mechanism. This mechanism is akin to how Earth's magnetic field is generated by the convection of molten iron in its outer core, but on a vastly more energetic and intense scale. In this setting, the rapid rotation and fluid motions can twist and stretch magnetic field lines, boosting their strength exponentially. Moreover, magnetars may also form through the differential rotation of various internal layers within the neutron star. This differential spinning further twists magnetic field lines and can result in fields of extreme strength. Over time, the intense magnetic stresses can lead to starquakes, sudden changes in the crust of the neutron star, which can cause outbursts of radiation across the electromagnetic spectrum. These phenomena are responsible for the high-energy emissions, such as X-rays and gamma rays, that we associate with magnetars. Additionally, the ultra-strong magnetic fields can influence the physics of the neutron star's surface and atmosphere, potentially leading to complex phenomena such as the emission of the extraordinary bursts and flares we observe from these cosmic giants. The sheer power and mystery of magnetars continue to captivate astronomers, providing a natural laboratory for studying the extreme states of matter and the fundamental forces of nature. Gamma-ray bursts, GRBs, are among the most energetic and enigmatic phenomena in the universe, capable of outshining entire galaxies for brief periods. They come in two primary varieties, short-duration and long-duration bursts, each believed to have distinct origins. Long-duration gamma-ray bursts, typically lasting from a few seconds to several minutes, are often linked to the collapse of massive stars. When a star much more massive than the Sun exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core implodes, forming a neutron star or black hole, while the outer layers are expelled in a cataclysmic supernova explosion. In particular cases, this collapse can generate highly collimated jets of gamma rays that pierce through the star's outer layers and shoot into space at nearly the speed of light. If one of these jets is directed towards Earth, it is observed as a gamma-ray burst. These events are sometimes called collapses and usually occur in active star-forming regions of galaxies. Short-duration gamma-ray bursts, on the other hand, last less than 2 seconds and are thought to be the result of collisions or mergers between compact objects such as neutron stars or a neutron star and a black hole. When these incredibly dense objects spiral into each other, driven by gravitational wave radiation, they eventually collide and merge, releasing an enormous amount of energy in the form of gamma rays, as well as gravitational waves. These violent mergers lead to the formation of a rapidly spinning black hole or a highly magnetized neutron star, known as a magnetar, surrounded by an irradiated high-energy debris field. Both types of GRBs send bursts of gamma radiation across the cosmos, briefly becoming the brightest sources of electromagnetic radiation in the observable universe. Thanks to satellites like NASA's Swift and Fermi missions, astronomers can now detect and study GRBs in unprecedented detail, capturing the afterglow in various wavelengths and pinpointing their host galaxies. Such observations are invaluable, enabling scientists to investigate these cataclysmic events and their roles in the evolution of the universe. Whether heralding the death of massive stars or the violent unions of compact objects, gamma-ray bursts continue to be dazzling messengers from the farthest reaches of our cosmos. Binary star systems, where two stars orbit a common center of mass, undergo complex and fascinating evolutionary processes over millions or even billions of years. These systems can vary greatly in terms of the masses and initial distances between the stars, leading to diverse evolution scenarios. The interaction between the stars can significantly alter their life cycles compared to solitary stars. Initially, both stars in a binary system typically form from the same cloud of gas and dust, starting their lives on the main sequence where they fuse hydrogen into helium. The more massive star evolves faster, eventually exhausting its hydrogen fuel and expanding into a red giant. If the stars are close enough, this expansion can lead to mass transfer, where the red giant loses material to its companion. This can lead to several outcomes. The companion star may gain enough mass to significantly alter its own evolution, potentially becoming more massive and luminous. Alternatively, the mass transfer process can strip the red giant's outer layers, exposing its core and forming a white dwarf. In some cases, the mass transfer can be so intense that it leads to dramatic events like novae, or even type Ia supernovae if the receiving star is also a white dwarf. Another intriguing possibility is the formation of X-ray binaries, where the companion star may end up as a neutron star or black hole. As the stellar remnants accrete matter from the companion star, they emit intense X-rays and other high-energy radiation. As the stars in the binary system continue to evolve, gravitational interactions can lead to phenomena such as tidal locking, where the star's rotational periods synchronize with their orbital periods. always showing the same face to each other. Over very long timescales, gravitational radiation can cause the binary orbit to decay, bringing the stars closer together. If the system comprises compact objects like white dwarfs, neutron stars, or black holes, this orbital decay can eventually lead to mergers, culminating in powerful events such as gravitational wave emissions or even gamma-ray bursts. Through these diverse pathways, binary star systems illustrate the intricate ballet of stellar evolution, significantly enriching our understanding of astrophysical processes and the life cycle of stars. Observing and modeling these systems continue to be a frontier in astrophysics, revealing the interconnected and dynamic nature of our cosmos. Tabby's star, officially known as KIC 84628552, has fascinated astronomers and the public alike due to its unusual and highly irregular brightness variations. Discovered using data from the Kepler Space Telescope, this star's light dips by up to 20% in a seemingly random and unpredictable manner, far more than can be explained by an orbiting planet's transit. Multiple hypotheses have been proposed to account for this mysterious behavior, and ongoing observations are gradually narrowing down the possibilities. One leading theory suggests that the variability might be due to a large, irregular swarm of cometary fragments orbiting the star. These fragments, potentially remnants of a broken-apart comet or comets, could periodically block the starlight in complex ways as they move in and out of our line of sight. This would account for the deep and irregular dips in brightness, which are not characteristic of known exoplanet transits. Another plausible explanation involves an uneven distribution of dust or debris in the circumstellar disk surrounding Tabby's star. Such a disk could be the aftermath of the star's interaction with another object or result from the gradual disintegration of a large body, creating clumps and clouds of material that intermittently obscure the star. Infrared observations have not strongly supported this theory, but it remains a viable candidate. Additionally, intrinsic stellar variability, possibly from large star spots or magnetic activity, is another consideration. However, the pattern and scale of the observed dimming events seem too erratic and profound to be solely attributed to stellar activity. The most exotic hypothesis, which initially captivated many, is the possibility of a massive structure created by an advanced civilization, sometimes called a Dyson swarm. While this idea has spurred significant interest and media attention, subsequent studies, including searches for accompanying radio signals or infrared emissions typical of technological activity, have found no evidence to support this theory. Continued observations across multiple wavelengths and the incorporation of data from other telescopes like the Gaia spacecraft help to add pieces to the puzzle. Whatever the cause, Tabby's star remains a compelling object of study in astrophysics, pushing the boundaries of our understanding of stellar behavior and the cosmic phenomena that can influence it. Blue stragglers present an intriguing anomaly in the study of star clusters, particularly in densely populated globular clusters. These stars appear unusually young, hot, and blue compared to their stellar companions, which should all have roughly the same age since they formed together. Their presence in clusters, where most stars are expected to be old, red giants, has puzzled astronomers for decades. Several theories have emerged to explain how blue stragglers manage to retain their youthful appearances. One prominent theory posits that blue stragglers form through stellar collisions within the crowded environments of globular clusters. In these clusters, stars are packed so closely together that gravitational interactions are frequent. When two stars collide and merge, the resulting star can have a rejuvenated appearance. This merging process effectively combines the mass of the two stars into a single, more massive star, which then behaves as if it were younger, burning hot and blue. Another explanation involves mass transfer in binary star systems. In a binary system, one star can evolve more quickly, transforming into a red giant and beginning to lose its outer layers. If the stars are close enough, this material can be transferred to its companion star, significantly increasing the mass and extending the lifespan of the recipient star. This mass transfer can strip away the older star's outer layers while inflating its companion into a more massive, hotter, and bluer star, a blue straggler. These processes are not mutually exclusive, and both stellar collisions and mass transfer likely contribute to the population of blue stragglers observed in various clusters. Advances in observational techniques, particularly high-resolution imaging and spectroscopy, allow astronomers to investigate these stars in greater detail, providing insights into their masses, compositions, and orbital dynamics within the clusters. Through such detailed studies, astronomers can better understand the frequency and conditions under which these intriguing stars form. Blue stragglers offer a unique glimpse into the dynamic lives of star clusters, revealing the importance of gravitational interactions and stellar evolution in shaping the characteristics of these ancient stellar populations. These stars continue to serve as a natural laboratory for studying complex physical processes, helping us understand the intricacies of stellar life cycles and the gravitational ballet that governs star cluster evolution. Przybylski's star, or HD 101065, stands out as one of the most enigmatic stars in the night sky, primarily due to its unusual pulsations and peculiar chemical composition. Located in the constellation Centaurus, this star has puzzled astronomers ever since its discovery in the 1960s. Its pulsations, which are irregular and do not conform to the patterns typically observed in other stars, have become a focal point of study. The star belongs to a class known as rapidly oscillating AP-ROAP stars, which are chemically peculiar and possess strongly magnetic fields. The pulsations observed in Przybylski's star are believed to originate from slow, non-radial oscillations. These oscillations are influenced by the star's strong magnetic field, which disrupts the usual symmetry and propagates waves through the star's interior in complex patterns. Unlike normal radial pulsations, where a star expands and contracts uniformly like a breathing balloon, non-radial pulsations affect different parts of the star's surface and interior asymmetrically. Another standout feature contributing to Przybylski's star's unique pulsations is its exceptionally peculiar chemical composition. The star's spectrum reveals an unusual abundance of rare Earth elements such as strontium, europium, and neodymium, alongside an unexpected presence of elements like uranium and plutonium. This peculiar mix of elements affects the star's opacity and its internal structure, potentially altering how the pulsation waves travel through the star. Enhanced magnetic activity could further influence these pulsations by interacting with these uncommon elements and their ionization states. Moreover, the strong magnetic fields of ROAP stars can distort the pulsation modes. The magnetic field affects the gas dynamics within the star and modifies how acoustic waves propagate. This interaction can lead to complex, multi-mode pulsations that are challenging to decipher but offer a wealth of information about the internal magnetic structure and chemical makeup of the star. Together, these factors, the strong magnetic field, uncommon elemental abundances, and non-radial oscillations, create a unique set of conditions that produce the enigmatic pulsations of Przybylski's star. Ongoing studies, including precise spectroscopic measurements and magnetic field mapping, will continue to provide deeper insights into the mechanisms driving these unusual oscillations, shedding light on both the life cycle of chemically peculiar stars and the fascinating interplay between magnetism and stellar evolution. Betelgeuse, the red supergiant star located in the constellation Orion, has intrigued astronomers with its dramatic and rapid changes in brightness. While it's known for its inherent variability as a semi-regular variable star, the significant dimming episodes it occasionally undergoes are subjects of intense scientific scrutiny. These brightness fluctuations can be attributed to several concurrent phenomena affecting the star's behavior and appearance. One primary factor contributing to Betelgeuse's variability is its pulsation. As a red supergiant, Betelgeuse has an unstable atmosphere that expands and contracts in cycles. These pulsations can cause changes in the star's surface temperature and size, leading to variations in brightness. When the star expands, the surface area increases but cools slightly, resulting in a dimmer appearance. When it contracts, the surface area decreases and the temperature rises, making the star appear brighter. Additionally, convection in Betelgeuse's extensive outer layers plays a significant role. The star has massive convection cells, akin to boiling on a grand scale, which can bring hot gas from the interior up to the surface, causing localized brightening. Similarly, when cooler gas descends, it can create temporary dark spots or regions, influencing the overall brightness. A particularly noteworthy event occurred between late 2019 and early 2020, when Betelgeuse experienced an unprecedented dimming, dropping to about 60% of its usual brightness. This episode, sometimes referred to as the Great Dimming, was later attributed to a combination of factors. Detailed observations revealed that the star had ejected a large amount of material, forming a dust cloud that temporarily obscured part of its light from our vantage point. This mass ejection produced a transient, circumstellar dust cloud that effectively shaded the star, leading to the significant drop in luminosity observed. Furthermore, Betelgeuse's evolutionary stage also contributes to its variability. As an aging red supergiant, it is nearing the end of its life and will eventually explode as a supernova. This advanced stage of stellar evolution is characterized by instability and mass loss, both of which can lead to temporary changes in brightness. By combining data from ground-based telescopes and space observatories, astronomers continue to monitor Betelgeuse closely. These observations not only provide insights into the mechanisms behind its dramatic brightness changes, but also offer a rare glimpse into the late stages of stellar evolution for massive stars, helping us better understand the processes leading up to supernova explosions. Epsilon Aurigae, a star system long shrouded in mystery, exhibits periodic dimming every 27 years, lasting for about 2 years each time. This fascinating phenomenon has intrigued astronomers for over a century. The periodic dimming is now understood to result from a large dark object passing in front of the primary star, eclipsing it from our line of sight. This object is not a typical planet or star, but rather a complex and intriguing structure. The primary component of Epsilon Aurigae is a luminous F-type supergiant star. The large dark eclipsing object has been identified as a massive disk of dust, likely surrounding a secondary companion. This companion is believed to be an evolving binary system itself, possibly comprising 2 stars orbiting each other within the dense, opaque disk. The disk is quite immense, estimated to be around 8 astronomical units in diameter, comparable to the orbit of Jupiter around the Sun. Its thickness and density are sufficient to block a significant portion of the primary star's light during the eclipse, causing the observed dimming. The precise nature of the secondary component and the disk has been the subject of extensive research. Observations suggest that the disk may be edge-on from our perspective, allowing us to see the extent of the dimming as it moves across the bright face of the supergiant. This orientation not only explains the periodic dimming, but also the duration of the eclipse, as the disk takes 2 years to completely traverse the star's disk due to its vast size. Further evidence supporting this model comes from detailed spectroscopic studies, revealing that the disk is composed of dust and gas, contributing to its opacity. During the eclipse, variations in the observed light can also be detected, attributed to inhomogeneities within the disk, such as denser regions or gaps. In addition to the primary eclipse, subtle brightening and darkening events have been observed, likely caused by the interaction between the light from the supergiant star and the structure within the disk. The study of Epsilon Aurigae reveals not only the fascinating dynamics of binary star evolution, but also the complex processes of disk formation and behavior in such unique systems. By continuing to monitor and model the system, astronomers hope to refine their understanding of the secondary companion and its enigmatic disk, unearthing more details about their composition, structure, and evolution. Epsilon Aurigae stands as a testament to the ongoing quest for knowledge about the intricate dance of celestial bodies. Within the astronomical community, certain binary systems like the well-studied Algol have long puzzled scientists by seeming to defy established stellar evolution theories. Algol, often referred to as the demon star, consists of a bright primary star and a dimmer, less massive companion. According to traditional theories of stellar evolution, the more massive star should have evolved faster, becoming a red giant, while its less massive companion remained on the main sequence. Instead, we observe the reverse, the less massive star appearing younger and still on the main sequence, while the secondary star appears older and more evolved. This apparent contradiction in our understanding is explained by the process of mass transfer within the binary system. At some point in its evolution, the originally more massive star expanded into a red giant and began transferring its outer layers to its less massive companion. This mass transfer altered the evolutionary paths of both stars. The recipient star, now more massive, increased in brightness and temperature, appearing younger despite its actual age. On the other hand, the donor star lost much of its mass and was left with a smaller, older core. This scenario provides a compelling explanation of why Algol's stars defy initial expectations, revealing the intricate and fascinating dance of stellar evolution influenced by the presence of a close companion. The origins of ultra-high energy cosmic rays, particles with energies exceeding 1 quintillion electron volts, remain one of the most tantalizing mysteries in modern astrophysics. These cosmic bullets strike Earth's atmosphere with such force that they generate extensive air showers, creating cascades of secondary particles observable by ground-based detectors. Evidence suggests that such extraordinary energies can't be produced within our Milky Way, implying an extragalactic origin. Several hypotheses propose that ultra-high energy cosmic rays are accelerated by the violent processes occurring in active galactic nuclei, where supermassive black holes at the centers of galaxies spew out enormous jets of particles and energy. Another popular theory points to gamma-ray bursts, GRBs, colossal explosions marking the deaths of massive stars or the merging of neutron stars as potential sources. These cataclysmic events release unimaginable amounts of energy, which could feasibly accelerate particles to ultra-high energies. Magnetic fields in these violent environments would whip particles to tremendous speeds, sending them careening across vast intergalactic distances to eventually collide with Earth's atmosphere, thus giving us glimpses into some of the universe's most extreme energetic processes. Cosmic rays, high-energy particles from outer space that bombard Earth's atmosphere, might have more influence on our planet than initially imagined. When these particles strike the Earth's atmosphere, they instigate a cascade of secondary particles and contribute to cloud formation by ionizing air molecules, which can act as nuclei around which water vapor condenses. An increase in cosmic ray flux may enhance cloud cover, which reflects sunlight and potentially cools the Earth's surface. Conversely, a decrease in cosmic rays could lead to fewer clouds, more sunlight reaching the surface, and a warming effect. This interplay indicates that cosmic rays could have a subtle but significant influence on climate patterns, although this area of research is still under active investigation. On the biological front, cosmic rays have a notable impact on life, particularly through their interactions with DNA. When high-energy particles hit living tissues, they can cause ionization that leads to genetic mutations. While most organisms have evolved mechanisms to repair DNA damage, the relentless bombardment over eons has undoubtedly influenced evolutionary processes. It's fascinating to consider that cosmic rays may have contributed to genetic variation, occasionally resulting in beneficial mutations that drive the diversity of life. However, they can also increase the risk of cancer and other health issues in humans, particularly for astronauts exposed to higher levels of cosmic rays outside Earth's protective magnetic field. Thus, while cosmic rays might seem an abstract cosmic phenomenon, they exert tangible effects on both our climate and the life forms that inhabit our planet. Cosmic rays, some of the most mysterious particles in the universe, achieve near light speed through a variety of high-energy astrophysical processes. The sheer velocity of these particles often requires immense energy, typically provided by some of the most violent and dynamic environments in space. One of the primary mechanisms thought to be responsible for this acceleration is shockwaves generated by supernovae, the cataclysmic explosions that mark the death of massive stars. When a star goes supernova, it releases an enormous amount of energy, creating shockwaves that can propel particles to astonishing speeds. These shockwaves act like natural particle accelerators, pushing charged particles to velocities near the speed of light. Active galactic nuclei also play a crucial role in accelerating cosmic rays to such extreme speeds. Situated at the centers of galaxies, AGNs are powered by supermassive black holes that consume vast amounts of matter. This infall generates powerful jets of particles that can extend for millions of light years. The intense magnetic fields within these jets whip particles around, accelerating them to ultra-high energies. Similarly, gamma-ray bursts, GRBs, the explosive outcomes of star collapses or neutron star mergers, provide another mechanism. These bursts are brief but extraordinarily intense, releasing colossal amounts of energy that can propel particles to near light speed. Together, these astrophysical events create a celestial laboratory, demonstrating nature's capability to achieve particle accelerations that dwarf our most advanced human-made accelerators. Cosmic rays, those high-energy visitors from various astrophysical phenomena, interact with the interstellar medium, ISM, in several fascinating ways. When these energetic particles encounter the ISM, which is composed of gas, dust, and cosmic plasma, they engage in complex processes that affect both the cosmic rays and the medium itself. One significant interaction is ionization. As cosmic rays travel through the ISM, they ionize atoms and molecules by stripping away their electrons. This ionization process plays a crucial role in maintaining the electrical charge balance in interstellar space and can influence the chemistry of the ISM by creating a variety of ionized species that participate in further chemical reactions. Another important interaction involves the generation of secondary particles. When cosmic rays collide with nuclei in the ISM, they can produce a cascade of secondary particles, including pions and muons. These interactions also lead to the creation of gamma rays, which can be detected by telescopes and provide valuable information about the processes occurring in space. Additionally, cosmic rays contribute to heating the ISM, especially in regions with low-density gas. The energy deposited by cosmic rays can affect the temperature and pressure of interstellar clouds, potentially influencing star formation rates. The interplay between cosmic rays and the ISM underscores the dynamic and interwoven nature of our galaxy, where high-energy particles from distant sources continuously shape and are shaped by the sprawling tapestry of interstellar matter. The terms knee and ankle in the cosmic ray spectrum refer to notable features where the flux of cosmic rays, plotted against their energy, exhibits sudden changes in slope. These features provide crucial clues about the origin and propagation of cosmic rays. The knee occurs around an energy of approximately 1 quadrillion electron volts. This feature is believed to be related to the limits of acceleration mechanisms within our galaxy. One leading hypothesis posits that the knee marks the energy beyond which supernova remnants, long considered to be primary accelerators of cosmic rays, can no longer effectively accelerate particles. As cosmic rays reach higher energies, they struggle to be confined by the magnetic fields within the remnants, leading to a steeper drop in their abundance beyond the knee. Additionally, at these energies, particles begin to escape the galaxy's magnetic field more easily, reducing their likelihood of being detected on Earth. The ankle, appearing at even higher energies, around 10 quintillion electron volts, presents a different puzzle. This feature is often interpreted as the transition point, where the dominant sources of cosmic rays switch from galactic to extragalactic origins. Above this energy, cosmic rays are thought to emanate from powerful extragalactic sources, such as active galactic nuclei or gamma-ray bursts. These ultra-high energy particles traverse vast intergalactic distances, and their observed flux is influenced less by galactic confinement and more by the universe's large-scale structure and magnetic fields. The ankle signifies where the flux flattening occurs, hinting at the arrival of cosmic rays from sources far beyond our Milky Way, thus bridging our understanding of both galactic and extragalactic cosmic phenomena. Solar cosmic rays and galactic cosmic rays, while both high-energy particles, originate from distinctly different sources and possess unique characteristics that set them apart. Solar cosmic rays, also known as solar energetic particles, SEPs, are primarily generated by the Sun. These particles are typically accelerated during solar flares and coronal mass ejections, CMEs, events that release immense amounts of energy and propel charged particles, mainly protons and helium nuclei, out into the solar system. Solar cosmic rays tend to have relatively lower energies compared to their galactic counterparts, usually in the range of tens to hundreds of millions of electron volts. The intensity of SEPs is often related to the solar cycle, peaking during periods of high solar activity, which occurs approximately every 11 years. On the other hand, galactic cosmic rays, GCRs, originate from far outside our solar system, likely from supernova remnants, pulsars, and other high-energy astrophysical sources scattered throughout our galaxy. These particles travel vast distances through the interstellar medium before reaching Earth, and are composed of a broader array of elements, ranging from hydrogen to heavier elements like iron. Unlike solar cosmic rays, GCRs possess incredibly high energies, often reaching billions and even trillions of electron volts. Their interaction with the Earth's atmosphere and magnetic field contributes significantly to the background radiation experienced at ground level and high altitudes. Furthermore, because of their differing origins, solar and galactic cosmic rays interact with the heliosphere, the bubble-like region of space dominated by the solar wind, in unique ways. The solar wind modulates the flux of GCRs, with solar activity influencing how many galactic cosmic rays can penetrate deep into the inner solar system. During periods of high solar activity, the enhanced solar wind and magnetic field provide a greater shielding effect, reducing the intensity of GCRs that reach Earth. Conversely, low solar activity correlates with increased GCR flux. Understanding these variations is crucial for activities such as space exploration, where both types of cosmic rays pose radiation hazards to astronauts and spacecraft. Supernova remnants SNRs play a pivotal role in the acceleration of cosmic rays, serving as some of the most powerful natural particle accelerators in the galaxy. When a massive star reaches the end of its life, it undergoes a catastrophic explosion known as a supernova, releasing a tremendous amount of energy and stellar material into space. The resulting expanding shock waves plow through the surrounding interstellar medium, creating the structure known as a supernova remnant. These shock waves are the key to accelerating particles to the high energies characteristic of cosmic rays. Within the shock front of a supernova remnant, the process of diffusive shock acceleration takes place. As particles, primarily protons and atomic nuclei, encounter the shock wave, their energies increase significantly through repeated interactions with the magnetic fields. These particles gain energy by crossing and recrossing the shock front, colliding with turbulent magnetic fields on both sides of the shock. With each crossing, their velocity increases, effectively turning the shock front into a formidable particle accelerator. This process continues until the particles reach relativistic speeds, nearing the speed of light, and are eventually able to escape the magnetic confinement of the remnant and propagate across the galaxy as cosmic rays. Observations of certain supernova remnants, such as Cassiopeia A and Tycho, have provided substantial evidence supporting this acceleration mechanism. High-energy gamma rays detected from these remnants are believed to be produced by the interactions of accelerated particles with the surrounding matter and magnetic fields. These gamma rays serve as indirect evidence of the presence of high-energy cosmic rays. Supernova remnants, therefore, not only contribute significantly to the pool of galactic cosmic rays, but also play a crucial role in our understanding of the processes that govern high-energy astrophysics and the life cycle of stars. Cosmic rays, which are high-energy particles originating from sources such as the Sun, supernova remnants, and distant galaxies, have a significant impact on space weather, a collection of conditions and phenomena in space that can affect Earth and its technological systems. Primarily, cosmic rays interact with the space environment around Earth, contributing to the complex dynamics of the heliosphere, magnetosphere, and ionosphere. In the heliosphere, the bubble-like region of space influenced by the solar wind, cosmic rays are modulated by the solar activity cycle. During periods of high solar activity, the enhanced solar wind and stronger solar magnetic fields act as a shield, reducing the influx of galactic cosmic rays. Conversely, during solar minimums, when solar activity is lower, the heliospheric shielding effect diminishes, leading to an increased flux of cosmic rays reaching Earth's vicinity. These variations in cosmic ray intensity influence the overall radiation environment in space, which is a critical consideration for spacecraft electronics and the health of astronauts. Cosmic rays also play a role in generating space weather disturbances by interacting with Earth's magnetosphere and ionosphere. When high-energy cosmic rays enter the atmosphere, they produce secondary particles, such as neutrons and muons, that can penetrate deep into the atmosphere and even to the surface. These secondary particles can induce transient ionization bursts in the ionosphere, affecting radio signal propagation and GPS accuracy. Additionally, cosmic rays can affect the formation and dynamics of clouds, potentially influencing weather patterns and climate over longer timescales. The continuous bombardment of cosmic rays thus underscores the need for advanced space weather forecasting and mitigation strategies, ensuring the protection of both technological infrastructure and human activities in space. Cosmic rays serve as natural probes into the composition and processes of distant galaxies, providing valuable insights that would otherwise be difficult to obtain through traditional electromagnetic observations. When cosmic rays, which are high-energy particles such as protons, electrons, and atomic nuclei, travel through space, they carry with them signatures of the environments they originated from. By analyzing these particles once they reach Earth, scientists can infer important details about the distant astrophysical sources from which they emanated. The composition of cosmic rays, particularly the proportion of different atomic nuclei, can reveal the elemental abundances in distant galaxies. For instance, the presence of elements heavier than hydrogen and helium, such as carbon, oxygen, silicon, and iron in cosmic rays, indicates the processes of stellar nucleosynthesis and supernova explosions in their source regions. These heavy elements are forged in the cores of stars and released into the galaxy through supernova explosions, spreading the building blocks for planets and life. Therefore, the elemental composition of cosmic rays can offer clues about the star formation rates, types of stars, and the overall chemical evolution of the galaxies they originated from. Furthermore, the energy spectra and isotopic composition of cosmic rays provide additional layers of information. Variations in the energy and isotopic ratios of cosmic rays can inform us about the acceleration mechanisms at play in distant astrophysical sources, such as supernova remnants or active galactic nuclei. The propagation of these high-energy particles through the interstellar and intergalactic medium also leaves distinct imprints, such as spallation reactions, where cosmic rays collide with interstellar atoms, breaking into lighter elements and isotopes that can be detected upon their arrival at Earth. Ultimately, cosmic rays offer a unique window into the distant cosmos, revealing the intricate processes governing the life cycle of matter on both galactic and intergalactic scales. Cosmic rays, those high-energy particles from outer space, interact intriguingly with Earth's magnetic field, shaping their trajectories and influencing their impact on our planet. As these particles, which include protons, electrons, and atomic nuclei, approach Earth, they encounter the geomagnetic field, a dynamic and protective shield generated by the movement of molten iron within our planet's core. When cosmic rays enter the vicinity of Earth, their paths are altered by the magnetic field due to the Lorentz force, which acts perpendicular to both their velocity and the magnetic field lines. This interaction causes charged particles to spiral and bend along the magnetic field lines, making it harder for them to penetrate directly to the surface. The effectiveness of the shielding is not uniform. It varies with latitude and the strength of the local magnetic field. Near the equator, where the magnetic field is strongest and horizontal to Earth's surface, cosmic rays are more likely to be deflected. In contrast, near the poles, where the magnetic field lines converge and are more vertical, cosmic rays can more easily penetrate the atmosphere. This interaction explains why we observe higher counts of cosmic rays at higher latitudes and altitudes, forming what we call the polar cusps and auroral zones. In these polar regions, the geomagnetic protection is less effective, allowing more cosmic rays to interact with the atmosphere. This interaction can create secondary particles, leading to phenomena like the auroras and contributing to the ionization levels in the polar atmosphere. The variations in cosmic ray flux influenced by Earth's magnetic field are crucial not just for studying space weather impacts, but also for understanding radiation exposure risks for both high-altitude aviation and space missions, underscoring the critical role of our planet's magnetic shield. The question of what caused the initial conditions of the Big Bang delves into one of the most profound mysteries in cosmology and physics. Traditional Big Bang theory describes the universe's early state as a singularity, a point of infinite density and temperature where the laws of classical physics break down. However, what triggered this singularity is an area of ongoing research and theoretical exploration. One prominent hypothesis is the idea of quantum fluctuations in a pre-existing quantum vacuum. According to quantum mechanics, even in the vacuum of empty space, there are temporary fluctuations due to the uncertainty principle, which may have sparked the Big Bang. In this scenario, a quantum fluctuation could have led to a rapid expansion through a process known as cosmic inflation. This inflationary period would have smoothed out the universe, explaining its large-scale homogeneity and isotropy, while also seeding the initial density fluctuations that eventually led to the formation of galaxies and other cosmic structures. Another intriguing theory posits the existence of a multiverse, where our universe is just one of many. In this framework, each universe can have its own set of physical laws and initial conditions, created through processes like eternal inflation. Here, different regions of spacetime can inflate at different rates, leading to bubble universes, each emerging from its own Big Bang-like event. Within this multiverse scenario, the conditions we observe in our universe are a result of random variations across these multiple universes. Both of these leading hypotheses, while compelling, remain speculative and are subjects of active research and debate. They attempt to push the boundaries of our understanding by merging principles from quantum mechanics and general relativity, suggesting that the conditions leading up to the Big Bang may reside in realms beyond our current observational capability. These theories highlight the quest in modern cosmology to uncover the origins of our universe, a journey that challenges our understanding of space, time, and the fabric of reality itself. The formation of the first stars and galaxies was a transformative epoch in the history of the universe, often referred to as the cosmic dawn. To understand this process, it's essential to begin with the aftermath of the Big Bang. Following this event, the universe was a hot, dense mixture of elementary particles and radiation. As it expanded and cooled over the next few 100,000 years, particles combined to form neutral hydrogen and helium atoms, leading to what is known as the recombination era. This era resulted in the decoupling of matter and radiation, allowing the universe to become transparent and enabling the formation of the cosmic microwave background, CMB, that we can observe today. The next significant phase was the Dark Ages, where the universe was filled with a diffuse gas of neutral hydrogen and helium. This period lacked visible light because no stars or galaxies had yet formed. However, during this time, tiny density fluctuations left over from the Big Bang began to grow under the influence of gravity, pulling gas into increasingly dense regions. These fluctuations, observed in the CMB, triggered the process of structure formation. As gravitational attraction continued to draw in material, the densest regions eventually collapsed to form the first stars, known as population 3 stars. These stars were likely much more massive than those seen today, given the lack of heavy elements, metals. They formed from nearly pure hydrogen and helium. The immense pressure and temperature in their cores ignited nuclear fusion, leading to the emission of light and ionizing radiation. This radiation began to ionize the surrounding hydrogen gas, marking the end of the Dark Ages and the beginning of the epoch of reionization. Simultaneously, the first stars grouped together to form proto-galaxies. As these stars lived and died, they enriched the interstellar medium with heavier elements through supernova explosions. This chemical enrichment allowed subsequent generations of stars to form with a broader range of masses and properties, further contributing to galaxy formation. Over time, these proto-galaxies merged and interacted, growing into the more extensive and complex galaxies we observe today. This cosmic choreography, driven by gravity and the intricate dance of particles and radiation, transformed an initially homogeneous universe into the richly structured cosmos filled with stars and galaxies. The epoch of reionization marks a transformative period in the universe's history, during which the first stars and galaxies transformed the intergalactic medium from a neutral state into one that is ionized. This epoch began roughly 400 million years after the Big Bang and lasted until about 1 billion years after the cosmic birth. During the Dark Ages, the universe was filled with neutral hydrogen and helium atoms, as the initial hot, dense state of the universe had cooled sufficiently for electrons to combine with protons and form neutral atoms. This created a largely opaque universe for much of the electromagnetic spectrum, as neutral hydrogen can absorb high-energy photons. As the first generation of stars, known as population 3 stars, began to light up, they emitted copious amounts of ultraviolet light. These massive stars, forming from nearly pristine hydrogen and helium gas, lived short, intense lives, producing high-energy photons capable of ionizing the surrounding hydrogen atoms. When these photons encountered neutral hydrogen, they would ionize the atoms, stripping electrons from protons and converting them into a plasma. As more stars formed and clustered into galaxies, their combined radiation fields gradually ionized larger and larger regions, creating bubbles of ionized gas around them. This reionization process wasn't uniform but rather patchy and gradual. Initially, isolated regions around individual stars and galaxies became ionized, but over time these ionized bubbles grew and merged, eventually leading to a predominantly ionized universe. The energy output from early black holes and quasars, the extremely luminous centers of young galaxies, also contributed to this reionization by emitting vast quantities of energetic radiation. Reionization had profound effects on the universe, enabling photons to travel more freely through space and gradually rendering the universe transparent to electromagnetic radiation across much of the spectrum. This allowed galaxy formation to proceed more efficiently and set the stage for the complex cosmic web of structures we observe today. Understanding the epoch of reionization provides critical insights into the formation and evolution of the first galaxies and the larger-scale structure of the universe. Current and upcoming telescopes, like the James Webb Space Telescope, aim to probe this enigmatic period further and illuminate the processes that end the cosmic dark ages. The asymmetry between matter and antimatter in the universe is one of the most intriguing unsolved problems in physics, often referred to as the baryon asymmetry problem. According to the Big Bang theory, the universe began with equal amounts of matter and antimatter. However, we observe a universe overwhelmingly dominated by matter, with very little antimatter. The mechanism behind this disparity remains a subject of extensive research and speculation. One leading hypothesis to explain this matter-antimatter imbalance involves a theoretical framework known as baryogenesis. This process would need to satisfy 3 critical conditions, known as Sakharov conditions, proposed by the Russian physicist Andrei Sakharov. These criteria are baryon number violation, C and CP violation, and a departure from thermal equilibrium. Under normal circumstances, the number of baryons, particles like protons and neutrons, is conserved. However, for matter to dominate over antimatter, processes that violate baryon number conservation must have occurred. Certain grand unified theories, GUTs, predict interactions that can change baryons into other particles, effectively violating baryon number conservation. For an asymmetry to develop, reactions must treat particles and antiparticles differently. Charge conjugation symmetry, C, transforms a particle into its antiparticle, and parity symmetry, P, involves flipping the spatial coordinates. Combined, CP symmetry would mean treating matter and antimatter symmetrically. However, experiments in particle physics, such as those involving K and B mesons, have shown that CP violation does indeed occur, albeit to a small degree, allowing for a slight preference for matter over antimatter in certain reactions. The universe underwent various phase transitions as it cooled. During these transitions, conditions deviated from thermal equilibrium, allowing time asymmetrical processes to preferentially produce more baryons, matter particles, than antibaryons. In an equilibrium state, any produced asymmetry would be instantly annihilated, but the dynamic conditions of the early universe provided the necessary environment for an imbalance to persist. Despite these compelling hypotheses, the exact nature of baryogenesis remains speculative and direct experimental evidence is still lacking. Physicists continue to explore various models, such as leptogenesis, which posits that an initial imbalance in leptons eventually led to the dominance of baryons through processes that are indirectly related. Some of the most promising research includes high-energy particle experiments, like those conducted at the Large Hadron Collider, LHC, and studies of neutrino properties, as these may hold clues to the mechanisms behind CP violation and other critical factors. ultimately solving the mystery of why there is more matter than antimatter could unlock new physics beyond the standard model, offering deeper insights into the fundamental workings of our universe and its origins. Imagine the universe just after the Big Bang, an era so chaotic and energetic that traditional physics struggles to describe it fully. This phase, known as cosmic inflation, occurred approximately 10 to the negative 33 seconds after the birth of the universe and lasted only until roughly 10 to the negative 32 seconds. During this incredibly brief period, the universe expanded exponentially, growing by a factor of at least 10 to the power of 26. This rapid growth happened faster than the speed of light, leaving behind a cosmos that was remarkably homogeneous and isotropic, despite originating from quantum fluctuations in an unimaginably small volume. Scientific consensus suggests that this inflationary phase was driven by a mysterious field called the inflaton, a concept rooted in quantum field theory. Theoretical physicists propose that the inflaton field had an energy density that remained nearly constant over time, causing space to stretch at an accelerating rate. As the inflaton field decayed, it released a tremendous amount of energy, essentially reheating the universe and setting the stage for the formation of particles and complex structures. This period of swift expansion solves many paradoxes of the early universe, such as the horizon and flatness problems, leading us to appreciate just how beautifully orchestrated the cosmos is, even in its most turbulent moments. The ultimate fate of the universe remains one of the most tantalizing questions in cosmology, with several compelling theories vying for prominence: the Big Freeze, the Big Rip, and the Big Crunch. Each scenario offers a distinct vision of an end-times cosmos. The Big Freeze posits that the universe's relentless expansion, driven by dark energy, will continue indefinitely. Over billions of years, galaxies will drift so far apart that starlight from one will no longer reach another. Stars will exhaust their nuclear fuel, turning into white dwarfs, neutron stars, or black holes. Eventually, even these remnants will evaporate or fall silent, leaving a dark, cold expanse where temperatures approach absolute zero and no thermodynamic work can occur. It's a bleak but gradual fading away of all cosmic activity. In contrast, the Big Rip theory forecasts a far more cataclysmic end. If dark energy tears the very fabric of space-time apart, herding galaxies, stars, planetary systems, and even atomic particles into infinite distances, this rupture could occur relatively swiftly. As the repulsive force of dark energy grows stronger, it would overpower all other forces, dismantling gravitationally bound systems, ripping atoms apart, and dissolving known structures back into a chaotic, featureless void. Then there's the Big Crunch, a fate where gravity ultimately wins the cosmic tug-of-war. Should the density of the universe prove sufficient to halt expansion, gravitational forces would reverse the process, pulling galaxies back together in a colossal collapse. This contraction would cause temperatures to soar and densities to climb, possibly leading to conditions reminiscent of the Big Bang. Some cosmologists speculate this might trigger a cyclic model of eternal oscillation, with the universe reborn from its ashes. Determining which of these scenarios will prevail depends on intricate measures of cosmic parameters, including the exact properties of dark energy, the universe's density, and its overall shape. As our observational tools sharpen, we edge closer to understanding how this grand cosmic narrative will ultimately conclude. Picture the cosmos as an intricate tapestry, woven from threads of dark matter and punctuated by luminous clusters of galaxies. The large-scale structure of the universe, a mind-boggling web of filaments and voids stretching across billions of light-years, traces its origins to minute quantum fluctuations that existed just moments after the Big Bang. During the epoch of cosmic inflation, these tiny variations in density were exponentially magnified, seeding the formation of what would become the vast cosmic structures we observe today. As the universe expanded and cooled, these initial density fluctuations caused matter to clump together under the relentless pull of gravity. This process formed the backbone of the cosmic web, an interconnected network of galaxies, clusters and superclusters separated by vast cosmic voids. Dark matter, an enigmatic substance comprising about 85% of the universe's mass, played a pivotal role in this grand design. Invisible and detectable only through its gravitational effects, dark matter provided the scaffolding upon which ordinary matter could gather and coalesce into stars and galaxies. Without dark matter's gravitational influence, the universe's visible structures would likely have never formed in the orderly patterns we observe today. As galaxies evolved and spread throughout the cosmos, they continued to interact and merge, further shaping the universe's large-scale structure. Observing the distribution and movement of galaxies allows cosmologists to trace the evolution of the cosmic web back to its primordial roots, giving us glimpses of an unfolding narrative that began in the dawn of time and continues to evolve, drawing our curiosity ever further into the mysteries of deep space. Primordial gravitational waves can be envisioned as ripples in spacetime, akin to the waves produced when a stone is dropped into still water. These ancient gravitational waves were generated during the first fleeting moments of the universe, specifically during the inflationary epoch. If detected, they would offer unambiguous evidence supporting the theory of cosmic inflation. The inflationary period, which started roughly 10 to the negative 33 seconds after the Big Bang and lasted until about 10 to the negative 32 seconds, saw the universe expand faster than the speed of light. This cataclysmic expansion not only stretched space but also amplified the quantum fluctuations present at the time. These fluctuations in space-time, frozen in by inflation, transformed into primordial gravitational waves. Unlike electromagnetic waves, which travel through space, gravitational waves are oscillations of space itself, making them incredibly elusive but deeply revealing about the universe's earliest moments. Intrinsic to the hunt for these primordial gravitational waves are the polarization patterns found in the cosmic microwave background, or CMB. The CMB is a relic radiation permeating the universe, originating from approximately 380,000 years after the Big Bang. Scientists analyze the B-mode polarization patterns within the CMB for the telltale swirling signatures that primordial gravitational waves would imprint. These patterns would indicate that spacetime was stretched and compressed in concert with inflation's rapid expansion, as predicted by inflationary models. Detecting these primordial gravitational waves would not only confirm that inflation occurred, but also provide crucial insights into the energy scale of inflation and the fundamental physics of the early universe. It would bridge our understanding from the macroscopic scale of cosmological structures down to the quantum fluctuations that seeded them, unveiling a deeper and more unified portrait of the cosmos. As technology and observational methods improve, the quest for these primordial waves remains one of the most riveting frontiers in modern cosmology. The Hubble tension refers to the perplexing discrepancy between different measurements of the universe's current rate of expansion, known as the Hubble constant. Two primary methods exist for determining this constant: direct measurements of the local universe using standard candles like Cepheid variables and type Ia supernovae, and indirect measurements derived from the cosmic microwave background, or CMB, using the standard model of cosmology and data from the early universe. Intriguingly, these methods produce differing results, with local measurements suggesting a faster expansion rate of around 73 kilometers per second per megaparsec, whereas CMB-derived methods yield a slower rate of about 67 kilometers per second per megaparsec. Resolving this tension requires a deep dive into both observational data and theoretical models. One possibility is that there's new physics beyond the current standard model of cosmology, known as lambda cold dark matter. For instance, the existence of another form of dark energy, or a modification to general relativity, could potentially reconcile the different measurements. Another hypothesis posits that there might be interactions between dark matter and dark energy that have yet to be understood, which could affect the expansion rate over time. Alternatively, the discrepancy could stem from systematic errors in one or both measurement approaches. Perhaps local measurements are influenced by unaccounted-for factors like cosmic dust, galactic foreground objects, or calibration issues with the standard candles. Similarly, CMB measurements might need reassessment in terms of the assumptions made about the early universe's condition and composition. Ongoing efforts to resolve the Hubble tension include refining measurement techniques, exploring intermediate distance indicators such as gravitational waves from neutron star mergers, and developing more comprehensive simulations that would better account for variables influencing both local and remote measurements. Ultimately, whichever path leads to the resolution of this cosmic quandary, it promises to deepen our understanding of the fundamental forces and constituents that shape our universe, potentially opening new realms of physics that connect the vast scales of cosmology with the quantum framework of the early universe. The quest to reconcile quantum mechanics with general relativity is one of the most ambitious and profound undertakings in modern theoretical physics. These two pillars of contemporary science describe nature on vastly different scales and frameworks. Quantum mechanics governs the microcosm of subatomic particles with unparalleled precision, while general relativity exquisitely explains the macroscopic realm of stars, galaxies, and the very fabric of space-time. One approach to unifying these frameworks is string theory, which postulates that the fundamental building blocks of the universe are not point particles, but rather tiny vibrating strings of energy. In string theory, particles are seen as different vibrational modes of these strings, each with precise properties and masses. This theory also requires additional spatial dimensions beyond the familiar three, typically amounting to a 10-dimensional universe. Although still hypothetical, string theory has the potential to elegantly merge the quantum and relativistic descriptions by providing a unified framework that encompasses both. Another promising avenue of research is loop quantum gravity. LQG attempts to quantize spacetime itself by envisioning it as composed of finite loops woven into a network or spin foam. In this model, spacetime possesses a discrete structure at the Planck scale, resolving some of the infinities that plague attempts to quantize general relativity directly. By incorporating quantized units of space and time, LQG seeks to provide a consistent picture of gravity compatible with quantum principles. Both approaches face formidable challenges, including making testable predictions that distinguish them from other theories and obtaining empirical validation through experiments or observations. However, the quest continues to push the boundaries of knowledge, spurring innovations in thought and technology. Future breakthroughs in high-energy particle physics, cosmological observations, and the study of black holes might provide crucial clues. The information paradox posed by black holes, whereby quantum information seemingly vanishes behind event horizons, already hints at the deep interconnections between gravity and quantum mechanics. As our observational instruments, such as gravitational wave detectors and particle accelerators, grow increasingly sophisticated, we edge closer to the elusive theory of quantum gravity that promises to unify the grand tapestry of the universe's forces and particles into a single coherent framework. Mars, with its rust-red surface and whisper-thin atmosphere, has long fascinated scientists and the public alike. One of the most intriguing mysteries associated with the red planet is the detection of methane emissions. Methane is a molecule that, on Earth, is often produced by biological processes, although it can also arise from geological activity. The presence of methane on Mars offers tantalizing clues that maybe, just maybe, the planet harbors life, or at least the conditions suitable for it. Multiple observations over the past 2 decades from both Earth-based telescopes and Mars-bound spacecraft like the European Space Agency's Mars Express and NASA's Curiosity rover have confirmed intermittent plumes of methane in the Martian atmosphere. These emissions fluctuate with the seasons and disappear quickly, suggesting an active and as yet unidentified process at work. There are 2 primary hypotheses to explain these methane emissions: biological activity and geological processes. The biological hypothesis posits that methane could be produced by microorganisms beneath the Martian surface, similar to methanogens on Earth that thrive in extreme environments like hydrothermal vents or deep underground. These microbes could reside in subsurface aquifers, shielded from the harsh surface conditions by meters of rock and soil. Although no direct evidence of life has been discovered on Mars, this theory remains tantalizingly plausible given Earth's own history with extremophiles. On the geological side, methane could result from serpentinization, a chemical reaction between water and certain types of rock like olivine and pyroxene, which are abundant on Mars. This process not only generates methane but also hydrogen, another potential energy source for life. Additionally, methane could be trapped in clathrate hydrates beneath the surface, releasing gas periodically due to changes in temperature or seismic activity. Resolving the origin of Martian methane is a top priority for ongoing and future missions. The upcoming ExoMars rover, a joint venture between ESA and Roscosmos, aims to drill up to 2 meters below the surface to search for signs of past or present life, as well as to understand the planet's geochemical processes better. As we continue to explore Mars, each new discovery brings us closer to solving the enigma of its methane emissions, potentially unlocking profound insights about the planet's capacity to support life and the dynamic processes shaping its environment. Ceres, the largest object in the asteroid belt between Mars and Jupiter, has captivated astronomers with its enigmatic brightness variations. These variations are most notably associated with bright spots that have puzzled scientists since the ancient dwarf planet was first observed in detail by NASA's Dawn spacecraft in 2015. The most striking of these features lies in the Occulta crater, where highly reflective material creates a dazzling contrast against the darker surface. The unusual brightness on Ceres is primarily due to deposits of sodium carbonate, a type of salt, as well as other evaporite minerals like ammonium chloride and sodium bicarbonate. These bright spots are thought to result from cryovolcanic activity, where briny water from Ceres' interior reaches the surface through fissures. Upon contact with the vacuum of space, the water rapidly sublimates, leaving behind these reflective salt deposits. This process of sublimation and deposition gives rise to the intense albedo variations observed from orbit. But why does this activity occur? The presence of these salts suggests that Ceres still harbors a subsurface ocean, or at least pockets of briny liquid water, kept from freezing solid by a combination of radioactive decay and residual heat from the dwarf planet's formation. When this pressurized brine finds a path to the surface, it erupts, creating bright deposits and contributing to the observed variability in brightness. Variation over time could also be influenced by diurnal cycles, with temperature fluctuations causing subtle changes in the surface composition or even transient atmospheres of water vapor. Another contributing factor could be impact events. Collisions with smaller asteroids can excavate these bright, salty materials from beneath the surface, drawing them into the sunlight where they temporarily shine brighter. As these exposed materials interact with space weathering processes, their albedo can change over time, adding to the seemingly dynamic and shifting appearance of Ceres. Understanding the brightness variations on Ceres provides invaluable insights into its geological history and internal structure. The findings offer compelling evidence that even small planetary bodies can exhibit complex, active geology, challenging traditional notions about the capabilities and limitations of such objects. Moreover, the presence of liquid water, even in the form of salty brine, raises intriguing possibilities about the potential for past or present habitability within our solar system, making Ceres an even more fascinating object of study. Enceladus, one of Saturn's most intriguing moons, boasts a surface marked by striking features known as tiger stripes, 4 parallel tectonic fractures located near its south pole. Discovered by the Cassini spacecraft, these enigmatic fissures have captivated scientists' imaginations and provided critical clues about the moon's dynamic nature. The tiger stripes are essentially massive cracks in Enceladus's icy shell, reaching hundreds of kilometers in length and roughly 1 to 2 kilometers wide. What sets them apart is their unusual thermal activity and their role as conduits for geysers that spew water vapor, icy particles, and organic compounds into space. These plumes are so significant that they contribute to Saturn's E-ring and suggest the presence of a subsurface ocean beneath the icy crust. The creation of these tiger stripes is thought to be driven primarily by tidal forces exerted by Saturn's strong gravity. Enceladus follows an elliptical orbit around Saturn, causing it to experience varying gravitational pulls that flex and strain its interior. This constant tidal stress generates frictional heat, which keeps parts of the subsurface ocean in a liquid state and creates the necessary conditions for the ice shell to crack. As the icy crust responds to these tidal forces, the The tiger stripes act as fault lines where the stress is relieved. The heat generated by the friction within these faults prevents them from refreezing completely, maintaining them as relatively warm, active regions. This warming not only keeps the fractures open, but also allows water from the subsurface ocean to rise through the cracks, erupting as geysers when it reaches the near vacuum of space. Interestingly, the repetitive cycles of tidal flexing and the ensuing geyser activity serve to rejuvenate and reshape the tiger stripes over time. This process might explain the relatively young age and fresh appearance of these features, contrary to the rest of Enceladus's older, heavily cratered surface. These findings, primarily gleaned from Cassini's close flybys and its suite of instruments, suggest that Enceladus is an active moon with a geothermal energy source capable of sustaining liquid water beneath its icy shell. The presence of organic compounds within the plumes further hints at the potential for habitability, making Enceladus one of the prime candidates in the search for extraterrestrial life within our solar system. The tiger stripes, therefore, are not just a striking geological curiosity, but a window into a hidden, dynamic world beneath the ice. Bennu, an ancient carbon-rich asteroid, presents an almost otherworldly appearance with its top-like diamond shape. The asteroid is roughly 500 meters in diameter and exhibits a bulging equatorial ridge, distinguishing it markedly from many other small celestial bodies. Understanding how Bennu acquired this peculiar shape requires delving into its formative processes and its journey through the cosmos. One prevailing hypothesis for Bennu's shape is the YORP, Yarkovsky-O'Keefe-Radzievsky-Paddock effect, a phenomenon that influences the spin rates of small bodies in the solar system. The YORP effect occurs when sunlight heats the surface of the asteroid and then re-radiates that energy as heat. This re-radiation produces a small but continuous torque, gradually altering the asteroid's rotation rate over millions of years. For Bennu, this process might have increased its spin rate to the point where centrifugal forces reshaped it, causing material to migrate toward the equator and form the distinctive ridge. Additionally, Bennu's shape is influenced by its rubble pile nature. Unlike monolithic asteroids, rubble pile asteroids are conglomerations of rocks, boulders, and dust held together by their mutual gravity rather than a single solid mass. This composition allows Bennu to be more malleable under centrifugal forces. As the asteroid's rotation increased, the loosely bound regolith would have moved outward and settled around the equator, further enhancing the ridge-like appearance. Impact events and subsequent seismic shaking also played a role in Bennu's formation. Collisions with other space debris cause vibrations that could help redistribute surface material, gradually influencing the shape over time. These impacts are a common occurrence in the chaotic environment of the asteroid belt, contributing to the ongoing evolution of small bodies like Bennu. Moreover, Bennu's geological history of being a fragment from a larger parent body must be considered. This parent body likely had a more complex and varied geological history, and the breakup could have imparted some initial angular momentum to Bennu, setting the stage for the subsequent YORP-driven evolution. NASA's OSIRIS-REx mission has provided unprecedented insights into Bennu, allowing for detailed mapping of its surface and analysis of its composition. The data gathered offers valuable clues about its formation and the processes shaping such bodies. Bennu's combination of a rapid rotation rate, rubble pile structure, and the influence of the YORP effect provides a coherent explanation for its unusual top-like shape. As scientists continue to analyze the data brought back to Earth, our understanding of Bennu, and by extension other similar asteroids, will become even clearer, shedding light on the dynamic and fascinating nature of these ancient solar system relics. Earth's magnetic poles, unlike the relatively stable geographic poles, are in constant motion due to the dynamic processes occurring deep within the planet. The mysterious shifts in Earth's magnetic poles can be attributed to the complex and turbulent flow of molten iron and nickel in the outer core, a phenomenon intricately linked to the geodynamo theory. At the heart of our planet lies a solid inner core composed primarily of iron and nickel, surrounded by a fluid outer core made of the same materials in a molten state. The movement of liquid iron and nickel in the outer core generates electric currents, which in turn produce magnetic fields. Due to the rotation of the Earth and the convective currents caused by heat escaping from the inner core, this molten metal flows in complex patterns, giving rise to a magnetic field that is both dynamic and intricate. These fluid motions in the outer core do not remain constant but rather change over time, leading to shifts in the main magnetic field. The magnetic poles, which are the points where the magnetic field lines are directed vertically downward, geomagnetic south, or upward, geomagnetic north, thus wander in response to these changes. This movement can be quite erratic, with the North Magnetic Pole currently traveling from the Canadian Arctic towards Siberia at a rate of approximately 50 to 60 kilometers per year. Another factor contributing to pole shifts involves geomagnetic secular variation, or the slow and gradual changes in the Earth's magnetic field over decades to centuries. These variations are influenced by the complex interaction of various processes within the outer core, including thermal and compositional convection, as well as the Coriolis effect due to Earth's rotation. Occasionally, the shifts are more dramatic, resulting in what is known as a geomagnetic reversal, where the magnetic north and south poles switch places. This phenomenon has occurred irregularly throughout Earth's history, with reversals happening roughly every few 100,000 years. During these transitions, the magnetic field weakens significantly and may exhibit a more complex, multipolar structure before the new polarity becomes established. Monitoring the magnetic field is crucial for understanding the behavior of the poles. Instruments like magnetometers on the ground and satellites in orbit continually measure the field's strength and direction, providing valuable data that helps scientists model the geodynamo processes. Earth's magnetic field not only protects us from harmful solar radiation, but also has practical applications, such as navigation. Understanding the causes behind the shifting magnetic poles not only satisfies scientific curiosity, but also informs how we interpret the magnetic signals in technologies that rely on the Earth's magnetic field. Oumuamua, the first known interstellar object to pass through our solar system, captivated scientists with its unusual characteristics, notably its unexpected acceleration. Discovered in 2017, this elongated Initial observations of Oumuamua revealed that its trajectory deviated subtly from what would be expected under the influence of gravity alone. Typically, such accelerations in cometary bodies are attributed to outgassing, where volatile substances like water, carbon dioxide, and other ices sublimate as the object approaches the Sun, creating jets that push the comet along. Another intriguing hypothesis involves solar radiation pressure. This idea posits that Oumuamua's acceleration might result from the cumulative effect of photons from the Sun pushing against the object's surface. For solar radiation pressure to account significantly for the acceleration, Oumuamua would need to have an incredibly low mass-to-area ratio akin to a light sail. This theory gained attention due to the object's unusual shape, thin and elongated, which could make it susceptible to solar radiation pressure. However, this would also imply that Oumuamua is far less dense than typical asteroids or comets, possibly nudging it toward the exotic category of space debris or a fragment from some larger, less dense structure. Understanding Oumuamua's unusual acceleration is challenging due to the limited observational window. Its fleeting passage through our solar system, combined with its high velocity, allowed for only a short period of detailed study. While both outgassing of volatile ices and solar radiation pressure remain viable explanations, each has its set of caveats and uncertainties. Oumuamua's unexpected acceleration intrigues both astronomers and physicists, highlighting the complex and diverse nature of cosmic visitors. It underscores the necessity of preparing for future interstellar objects, equipping us with improved observational tools and missions dedicated to rapidly identifying and studying these enigmatic travelers, which might hold the keys to understanding the broader dynamics of objects from beyond our solar system. The spokes in Saturn's rings are among the most mysterious and captivating features observed within the gas giant's magnificently complex ring system. These transient radial features appear as ghostly striations that rotate along with the ring particles, temporarily marring the otherwise smooth structure of Saturn's rings. Discovered by the Voyager spacecraft in the early 1980s and later studied in greater detail by the Cassini mission, these spokes are believed to be primarily electrostatic phenomena. The leading hypothesis for the creation of these spokes revolves around the interaction between the ring particles and Saturn's powerful magnetic field. The smallest particles in Saturn's rings, primarily dust-sized grains, can become electrically charged due to the interaction with solar ultraviolet radiation or energetic particles trapped in the planet's magnetosphere. As these tiny particles acquire an electric charge, they can be influenced by Saturn's magnetic field, causing them to lift slightly above the ring plane and align along magnetic field lines. This process involves several complex steps. First, when charged ring particles interact with the magnetic field, they experience a Lorentz force, which can lift them from the ring's surface. The lifted particles form the visible spoke structures by scattering sunlight differently than the surrounding uncharged particles, making spokes conspicuous against the background of the rings. The variations in light scattering cause the spokes to appear darker or lighter than the adjacent regions of the rings, depending on the angle of observation and illumination. Seasonal changes on Saturn also influence the formation and visibility of the spokes. They are more prominently observed around the equinoxes when Saturn's equatorial plane, and thus its rings, is aligned edge-on with the Sun. During these times, the Sun's ultraviolet radiation efficiently charges the ring particles, enhancing the conditions needed for spoke formation. As Saturn shifts through its seasons, the incidence and visibility of the spokes vary, explaining why they are not always observable. Another intriguing aspect of the spokes is their dynamic behavior. They can form and dissipate over a matter of hours or days, moving across the rings in synchronization with Saturn's rotation. This rapid formation and disappearance further indicate the delicate balance controlled by the interaction between electromagnetic forces and the material composition of the rings. Understanding the behavior and mechanics behind these spokes offers critical insights into the interactions between the solid and plasma environments within the ring system. These observations have broader implications for planetary ring systems and the study of dust dynamics in various astrophysical contexts, contributing to our knowledge of how electromagnetic forces can shape and influence celestial environments. Pluto's heart-shaped feature, known as Tombaugh Regio, stands as one of the most striking and iconic surface features on this distant dwarf planet. Named after Clyde Tombaugh, the astronomer who discovered Pluto in 1930, this vast region comprises two major lobes with distinct geological characteristics. The left lobe, called Sputnik Planitia, is an enormous basin filled with nitrogen, methane, and carbon monoxide ices, while the right lobe extends into rugged, mountainous terrain. The formation of Sputnik Planitia, the western lobe of Tombaugh Regio, is believed to be related to both endogenic and exogenic processes, meaning internal and external influences. A leading hypothesis suggests that Sputnik Planitia is the result of a massive impact event. Billions of years ago, an asteroid or comet could have struck Pluto, creating a huge basin. Over time, this basin became a cold trap for volatile ices due to its low elevation and the unique climatic conditions on Pluto. This accumulation of ices likely led to isostatic adjustment, where the crust rebounded and the basin's floor was infilled, creating the smooth, icy plains observed today. Interestingly, Sputnik Planitia is not just a passive deposit of ices, it is geologically active. The plain exhibits a pattern of polygonal cells, likely caused by convection within the nitrogen ice. These convective patterns suggest that the ice is slowly being renewed and resurfaced by the movement of material driven by the slow but steady heat emanating from Pluto's interior. This process hints at a surprising level of thermal activity for such a distant, cold world. The right lobe of Tombaugh Regio features a more rugged topography, consisting of a mix of nitrogen ice and water ice mountains. The formation of this terrain is less understood but may involve tectonic processes, sublimation, and the unique interplay between different types of ice. The region's geological diversity provides crucial clues about the interplay of internal and external forces shaping Pluto's surface. The prominent location of Tombaugh Regio near the equator and its role in influencing Pluto's climate also have significant implications. The bright ices of Sputnik Planitia reflect much of the sunlight, which helps to control the temperature and pressure of Pluto's thin atmosphere. This reflective surface can alter the sublimation and condensation cycles of nitrogen and other volatiles, impacting atmospheric dynamics and contributing to seasonal changes seen on Pluto. The New Horizons spacecraft, which flew by Pluto in 2015, provided the high-resolution images and data that unveiled the complexities of Tomball Regio. These observations highlighted unexpected geological activity and diverse surface compositions, challenging previous notions of what small, distant dwarf planets could be like. As scientists continue to analyze New Horizons data and develop models, our understanding of how Tomball Regio and similar features form will undoubtedly deepen, offering insights into planetary processes both within our solar system and beyond. The unusual radar reflections from Venus's highlands have intrigued scientists since they were first observed by the Magellan spacecraft in the early 1990s. These highlands, particularly regions like Maxwell Montes, exhibit highly reflective surfaces in radar images, far brighter than the surrounding lowlands. The cause of these radar reflections is a fascinating interplay of Venusian geology and atmospheric chemistry. One leading hypothesis attributes these unusual radar reflections to the presence of metallic or semi-metallic compounds on the highland surfaces. Venus's extremely high surface temperatures, which can reach around 465 degrees Celsius, about 870 degrees Fahrenheit, combined with its dense atmosphere rich in sulfuric acid and carbon dioxide, create a harsh environment where distinctive chemical reactions can occur. In these conditions, minerals may react with atmospheric gases and precipitate out on the cooler highland surfaces. Specifically, the reflective properties observed in radar data are consistent with materials like pyrite, also known as fool's gold, bismuth, or tellurium-bearing compounds. These materials can form through volcanic outgassing, releasing elements that later condense and settle on the highlands. For instance, the presence of sulfides like pyrite could result from sulfur gases emitted from volcanic activity, combining with metallic elements. Another contributing factor could be the presence of a substance that undergoes a phase change at the highland elevations. The cooler temperatures at higher altitudes on Venus, though still hot by Earth standards, could allow certain minerals or metallic compounds to form a solid-state frost, akin to how ice frost forms on Earth's surfaces. This solidified layer can enhance radar reflectivity, making the highlands appear much brighter than the surrounding terrains. Additionally, differences in surface roughness might play a role. Highlands could possess a rougher surface texture at smaller scales, scattering radar waves more efficiently and appearing brighter in radar images. Such enhanced scattering could result from a combination of geological processes like tectonic activity and erosion patterns unique to Venus's high-temperature, high-pressure environment. The data from Magellan's radar mapping, supplemented by observations from other missions like the Arecibo Observatory and Japan's Akatsuki probe, continue to help scientists refine their understanding of Venusian surface properties. Future missions, such as NASA's Veritas and ESA's Envision, aim to provide more detailed radar and spectroscopic studies, which may clarify the exact compositions responsible for the radar reflectivity and offer deeper insights into the geological and chemical processes shaping Venus's enigmatic highlands. Miranda, one of Uranus's innermost and most intriguing moons, showcases a remarkably patchwork-like surface, unlike any other celestial body in the solar system. This small moon, just about 480 kilometers, 300 miles in diameter, exhibits a bewildering array of geological features, including giant canyons, terraced layers, and regions known as coronae that appear as large racetrack-shaped bands. This unusual and diverse landscape is a testament to Miranda's complex and violent geological history. One leading hypothesis for Miranda's patchwork appearance is the occurrence of multiple episodes of tectonic activity and cryovolcanism. Early in Miranda's history, tidal forces from its interactions with Uranus and possibly other moons would have generated significant internal friction and heat. This process, known as tidal heating, could have caused the moon's interior to partially melt, leading to convective motion and surface deformation. The coronae, Miranda's most distinctive features, are thought to be the result of upwelling diapirs, which are blobs of warmer ice that rise through the colder, rigid ice shell. These diapirs would push up against the surface, creating the terraced and banded regions observed. The Miranda coronae have concentric ridges and troughs, suggesting that these upwellings caused the surface to stretch and crack, resulting in the distinctive patchwork regions. Additionally, Miranda's large canyons, some of which are up to 20 kilometers deep, might have formed from extensional tectonics, a stretching and fracturing of the crust powered by internal processes or tidal interactions. These enormous chasms could have also been exacerbated by past cryovolcanic activity, where volatile substances such as water, ammonia, or methane erupted through the surface, reshaping the terrain dramatically. Another hypothesis considers that Miranda might have undergone a form of catastrophic disruption and reaccretion. This scenario suggests that a significant impact could have shattered the Moon, causing it to break apart. The gravitational pull would then reassemble the fragments, creating a body with a highly varied and jumbled surface. This explanation helps account for the high degree of heterogeneity observed across Miranda's surface. Perhaps Miranda's most captivating feature is how it defies traditional geological expectations, showing evidence of resurfacing events across different epochs. The patchwork terrain likely records a tumultuous evolution marked by the interplay of endogenic, internal, and exogenic, external forces. Each geological unit on Miranda's surface appears to tell a story of different eras of tectonic and cryovolcanic activity, making it a fascinating subject for ongoing study. The data we have on Miranda is primarily from the Voyager 2 flyby in 1986, which provided detailed images and invaluable insights into this mysterious moon. Future missions to the Uranian system may offer further understanding of Miranda's geologic history, elucidating the intricate processes that have sculpted its uniquely captivating landscape. The origin of life on Earth is one of the most profound and intriguing questions in science, sparking numerous theories and extensive research. While definitive answers remain elusive, several leading hypotheses offer compelling scenarios for how life might have emerged from non-living chemical processes. One prevailing theory is the primordial soup hypothesis, which suggests that life began in a warm pond or ocean where a mixture of simple organic molecules was subject to energy sources such as ultraviolet light from the sun, lightning, or volcanic activity. This environment could have facilitated the formation of more complex molecules, eventually leading to self-replicating molecules like RNA. Experiments conducted by Stanley Miller and Harold Urey in the 1950s supported this idea by demonstrating that when a mixture of water, methane, ammonia, and hydrogen was exposed to electrical sparks, simulating lightning, amino acids, the building blocks of proteins, could form. Another influential theory is the hydrothermal vent hypothesis. This proposes that life may have originated around hydrothermal vents on the ocean floor, where mineral-laden water, heated by geothermal processes, meets cold ocean water. These environments are rich in energy and chemicals that could promote complex chemical reactions. Indeed, modern hydrothermal vents host diverse ecosystems that thrive without sunlight, relying entirely on chemosynthesis. This habitat creates the conditions where simple organic compounds could react and assemble into more complex molecules, leading to the first living cells. The RNA world hypothesis offers another perspective, positing that RNA, a versatile molecule capable of both storing genetic information and catalyzing chemical reactions, was a crucial step in the origin of life. RNA molecules might have formed spontaneously from simpler precursors and, due to their catalytic properties, could drive the synthesis of more RNA molecules, setting the stage for natural selection to favor more efficient replicators. Yet another intriguing idea is the concept of panspermia, which suggests that life's building blocks, or even life itself in a microbial form, could have originated elsewhere in the cosmos and been delivered to Earth via comets, asteroids, or meteoroids. This theory does not explain how life began, but rather shifts the location of its origin to other celestial bodies. Recent advances in synthetic biology and prebiotic chemistry have provided additional insights. Laboratory experiments have shown that under specific conditions, lipid molecules can self-assemble into vesicles resembling cell membranes, and that amino acids and nucleotides can form peptide bonds and nucleic acids, respectively. These findings suggest that simple protocells, structures that resemble living cells but lack true replication and metabolism, could have arisen from naturally occurring processes on the early Earth. Although each hypothesis has its strengths and challenges, they all contribute to a multifaceted understanding of how life could have originated. As research progresses, combining elements from these different theories may eventually paint a more comprehensive picture of the intricate chemical choreography that led to the dawn of life on our planet, opening new doors in the quest to understand our own origins and the potential for life elsewhere in the universe. Detecting alien life is one of the most exciting prospects in modern science, and identifying reliable biosignatures, indicators of life, is crucial to this quest. Biosignatures are characteristics, elements, molecules, or phenomena that provide scientific evidence of past or present life. Here are some of the most promising biosignatures that researchers are focusing on. One of the most significant biosignatures is the presence of *** oxygen and ozone ** in a planet's atmosphere. On Earth, oxygen is predominantly a product of photosynthetic organisms. If oxygen or ozone, which is formed by the interaction of oxygen with ultraviolet light, were detected in conjunction with other gases in the atmosphere of an exoplanet, it could hint at biological processes similar to those on Earth. However, it's important to note that non-biological processes could also produce oxygen, so this biosignature must be considered alongside other indicators. *** methane. *** is another promising biosignature. On Earth, methane is largely produced by biological processes such as microbial digestion, although geological processes can produce it too. The simultaneous presence of methane and oxygen in an exoplanet's atmosphere would be particularly compelling, as these two gases would typically react and neutralize each other, suggesting a continuous source possibly related to life. *** complex. Organic molecules, ***, serve as another potential biosignature. These include amino acids, lipids, and other carbon-based compounds that form the building blocks of life. Earth's organic molecules offer a baseline for what scientists might look for on other worlds, either through direct analysis of samples or spectroscopic techniques that identify specific wavelengths of light absorbed or emitted by these molecules. ***, water vapor. *** is not a definitive biosignature on its own, but its presence is crucial since all known life requires liquid water. Detecting water vapor, along with other potential biosignatures, enhances the likelihood of a habitable environment. Another interesting angle revolves around the concept of *** red edge ***, a specific increase in reflectance in the near-infrared spectrum associated with vegetation on Earth. If telescopes detect a similar spectral signature on an exoplanet, it could indicate photosynthetic organisms. Examining *** isotopic ratios. *** can also offer significant insights. Life tends to preferentially utilize lighter isotopes, leading to distinct isotopic signatures. For example, biological processes on Earth produce an overabundance of the lighter isotopes of carbon, nitrogen, and sulfur. Detection of anomalous isotopic ratios could suggest biological activity. *** atmospheric disequilibria *** are another compelling biosignature. Living organisms often produce mixtures of gases that would not naturally coexist in the same atmosphere without biological processes to maintain them. The simultaneous presence of gases like methane and oxygen, as previously mentioned, or hydrogen and oxygen, could point to ongoing biological activity. Advanced telescopes and missions such as the James Webb Space Telescope and upcoming exoplanet explorers like the European Space Agency's Ariel mission are honing in on these biosignatures. Additionally, missions targeting the icy moons of our solar system, such as NASA's Europa Clipper and ESA's JUICE mission to Jupiter's moon Ganymede, are designed to search for signs of life within the subsurface oceans. While each potential biosignature is intriguing on its own, the most convincing evidence of alien life will likely come from a combination of these indicators, reinforcing each other within the context of a planetary environment. The ultimate goal is to build a comprehensive profile that strongly suggests biological processes, enhancing our understanding of life's potential beyond Earth. The quest to determine the prevalence of Earth-like planets in the habitable zone, often described as a region where conditions might be just right for liquid water to exist on a planet's surface, continues to captivate astronomers. This region is crucial because liquid water is considered essential for life as we know it. Advances in space telescopes and observational techniques have significantly expanded our knowledge, bringing us closer to answering this profound question. Data from missions like NASA's Kepler Space Telescope have provided a wealth of information. Kepler, which operated from 2009 to 2018, monitored the brightness of over 150,000 stars, looking for periodic dimming that would indicate an exoplanet transiting in front of its host star. Through its observations, Kepler discovered thousands of exoplanets, including many smaller rocky ones similar in size to Earth. Current estimates based on Kepler data suggest that about 20 to 25% of Sun-like stars harbor at least one potentially habitable, Earth-sized planet within their habitable zones. Further insights come from the Transiting Exoplanet Survey satellite, launched in 2018, which continues the search for Earth-like planets around nearby stars. Complementing TESS, ground-based observatories and radial velocity method surveys contribute additional detections and confirmations of such planets, refining our understanding of their frequency. Despite these discoveries, not all planets found in the habitable zone are necessarily Earth-like. Size and location are only part of the criteria. The planet's atmosphere, magnetic field, geological activity, and water presence are crucial factors that determine its habitability. Additionally, the habitable zone's exact range varies depending on the type and activity of the host star. Red dwarfs, the most common type of star in our galaxy, have closer, narrower habitable zones compared to Sun-like stars, but they also exhibit high levels of stellar flares which can strip away planetary atmospheres. Considering the Milky Way contains an estimated 100 to 400 billion stars, the fraction of stars with potentially habitable planets suggests there could be billions of Earth-like planets in our galaxy alone. This estimation, while promising, is continually refined as more exoplanets are discovered and studied in detail. Astronomers also focus on nearby stars, such as the Proxima Centauri system, to understand the prevalence of Earth-like planets. Proxima Centauri b, a planet orbiting within the habitable zone of the closest star to our Sun, has garnered significant interest. While its exact conditions are still under study, its discovery supports the idea that such planets might not be rare. Future missions, like the James Webb Space Telescope, the European Space Agency's Plato mission, and increasingly advanced ground-based telescopes like the Extremely Large Telescope and the Giant Magellan Telescope, aim to provide more detailed observations. These instruments will help analyze the atmospheres of these Earth-like exoplanets for signs of habitability or even biosignatures, bringing us closer to determining just how common life-bearing worlds might be. Ultimately, while Earth-like planets in the habitable zone appear to be relatively common, confirming their true habitability requires detailed study. As our technology and methods continue to improve, we are likely to refine our understanding of these intriguing worlds and their potential to host life. The idea of life existing in the clouds of Venus is a tantalizing concept that has gained traction among some scientists, despite the planet's notoriously inhospitable surface conditions. Venus, with surface temperatures around 465 degrees Celsius, 869 degrees Fahrenheit, and atmospheric pressure 90 times that of Earth's, seems an unlikely place for life as we know it. However, its upper cloud layers offer a markedly different environment that might be more conducive to the possibility of life. The cloud tops of Venus exist at altitudes where temperatures range from about 30 to 70 degrees Celsius, 86 to 158 degrees Fahrenheit, and pressures are similar to those found at Earth's surface. This region presents a relatively milder environment compared to Venus's scorched surface. The clouds themselves are primarily composed of sulfuric acid droplets, which is hostile to most known life forms on Earth, but not necessarily beyond the realm of possibility for extremophiles, organisms that thrive in extreme environments. Interest in the clouds of Venus as a potential habitat for life surged in 2020 with the reported detection of phosphine gas, a molecule found on Earth as a result of either industrial processes or microbial activity. This discovery, made using the James Clerk Maxwell telescope and the Atacama Large Millimeter Submillimeter Array, suggested that some form of life could be producing phosphine. On Earth, phosphine is associated with anaerobic organisms, primarily bacteria living in oxygen-poor environments like swamps and the intestines of animals. The detection of phosphine, however, has been subject to significant scrutiny and debate. Some researchers have questioned the findings, citing potential issues with the observational data and the interpretation of the spectral lines. Regardless, the potential presence of a biosignature gas in Venus's atmosphere has reignited interest in the planet's cloud layers and spurred calls for further investigation. For life to exist in the acidic clouds of Venus, potential organisms would need specialized adaptations. Hypothetical life forms might possess biochemical mechanisms to tolerate, neutralize, or exploit highly acidic conditions. They could also use the particulate matter and the limited water vapor available in the atmosphere to sustain metabolic processes. In some scenarios, these life forms could exist within protective microhabitats or aerosols, essentially tiny droplets that provide a more habitable microenvironment within the broader acidic context. To explore these possibilities, upcoming missions are being designed specifically to study the atmosphere of Venus. NASA's Da Vinci Plus mission and the European Space Agency's Envision mission aim to provide detailed analyses of the planet's atmosphere, surface, and geological activity. These missions will deploy sophisticated instruments capable of detecting and analyzing trace gases, cloud particles, and atmospheric chemistry, offering deeper insights into the potential for life in the clouds of Venus. Understanding whether life can exist on Venus requires exploring a broad array of scientific questions and employing a suite of advanced technologies. While the environment is harsh by Earth standards, the notion that life might find a way to adapt to such extreme conditions continues to drive interest and research, pushing the boundaries of what we consider possible for habitability in the solar system. The potential for life in the subsurface oceans of icy moons within our solar system is one of the most intriguing frontiers in astrobiology. Notable moons such as Europa, orbiting Jupiter, Enceladus, orbiting Saturn, and Titan, also orbiting Saturn, harbor subsurface oceans beneath their icy crusts, offering environments that could be conducive to life. Europa, one of Jupiter's largest moons, is a prime candidate for hosting life. Beneath its ice-covered surface lies a global ocean of liquid water, estimated to be twice the volume of Earth's oceans combined. Evidence for this ocean comes from both the Galileo spacecraft's measurements and the Hubble Space Telescope's observations, which suggest the existence of plumes of water vapor erupting from cracks in the ice. Europa's ocean is thought to be in contact with a rocky seafloor, where hydrothermal vents could provide the necessary heat and nutrients for life. On Earth, hydrothermal vents teem with life, independent of sunlight, deriving energy from chemical reactions, a process known as chemosynthesis. If similar conditions exist on Europa, it could potentially support microbial or even more complex life forms. Enceladus, a smaller moon of Saturn, also boasts a subsurface ocean beneath its icy shell. The Cassini spacecraft provided detailed evidence of water ice plumes erupting from Enceladus's south polar region, indicating the presence of liquid water beneath the surface. These plumes contain complex organic molecules, salty water, and even tiny silica grains, which suggest hydrothermal activity at the ocean floor. The combination of liquid water, organic molecules, and energy sources makes Enceladus an incredibly promising site for the search for extraterrestrial life. Titan, another moon of Saturn, offers a unique environment with not just one but potentially two types of liquids, surface lakes and seas of liquid methane and ethane, and a hypothesized subsurface ocean of water. The surface hydrocarbons present a different chemistry for potential life forms, which might be based on methane solvents rather than water. However, the subsurface ocean, which could be similar in composition to the oceans of Europa and Enceladus, lies beneath a thick ice shell, making it an intriguing target for future exploration. The potential for life in these subsurface oceans depends on several factors, a stable environment with liquid water, the presence of essential chemical compounds like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and a source of energy. In the absence of sunlight, chemical energy from hydrothermal vents or chemical reactions involving the icy materials could support life. The discovery of organic molecules and potential energy sources in the plumes of Enceladus and on the surface of Europa strengthens the case for habitability. Future missions aim to explore these moons in greater detail. NASA's Europa Clipper, set to launch in the 2020s, will perform detailed reconnaissance of Europa's ice shell and subsurface ocean. It will focus on determining the moon's habitability by studying the ice thickness, ocean composition, and potential hydrothermal activity. Similarly, the proposed Enceladus Life Finder mission aims to directly sample the moon's plumes for signs of life. Titan will be the focus of NASA's Dragonfly mission, which will send a rotorcraft to explore its diverse surface and atmospheric chemistry. While it will not directly probe the subsurface ocean, it will investigate prebiotic chemistry and methane-based life hypotheses. The exploration of these icy moons offers the potential to uncover environments where life might exist beyond Earth, expanding our understanding of life's potential adaptability and resilience in extreme conditions. It holds the promise of answering one of humanity's most profound questions. Are we alone in the universe? Extremophiles, organisms that thrive in environments previously thought too extreme for life, have significantly broadened our understanding of where and how life can exist, thereby influencing the search for extraterrestrial life. These remarkable organisms not only redefine the limits of habitability on Earth, but also provide crucial insights into potential habitats and survival strategies for life elsewhere in the cosmos. One of the key lessons from extremophiles is that life can adapt to a wide range of environmental conditions, many of which are analogous to environments found on other planetary bodies. For instance, thermophiles and hyperthermophiles, which reside in extremely hot environments like hydrothermal vents on the ocean floor, suggest that similar habitats might exist on moons like Europa and Enceladus. The presence of hydrothermal activity in the subsurface oceans of these moons, combined with the potential for water-rock interactions, could create niches where microbial life similar to deep-sea extremophiles might thrive. Acidophiles and alkalophiles, which flourish in highly acidic or alkaline environments respectively, demonstrate that extreme pH levels are not a barrier to life. This insight is particularly relevant for the exploration of Venus, where the acidic cloud layers could harbor acid-tolerant microorganisms. Similarly, certain features on Mars, such as ancient lake beds with evidence of past acidic conditions, could have supported acidophilic life during wetter periods in the planet's history. Psychrophiles, organisms that live at very low temperatures, and cryophiles, which thrive in cold environments, offer clues about potential life on icy worlds. For example, the ice-covered lakes of Antarctica, where psychrophiles flourish, serve as terrestrial analogues for the frozen surfaces of Europa and Enceladus. These Earth-based environments help scientists understand how life might survive and adapt under perpetual ice, relying on available nutrients and energy sources derived from chemical reactions rather than sunlight. Xerophiles, which can withstand extreme desiccation, provide valuable models for studying potential life on Mars, where the surface is extremely dry. The discovery of brines and recurring slope lineae on Mars suggests that temporary wet conditions might exist, analogous to arid environments on Earth, where xerophiles can become metabolically active when water becomes available. Radiation-resistant organisms like Deinococcus radiodurans showcase the incredible resilience of life in the face of high levels of radiation. This trait is particularly pertinent for the potential habitability of Mars and Europa. On Mars, the thin atmosphere offers little protection from cosmic and ultraviolet radiation, making the survival strategies of radiation-resistant extremophiles particularly relevant. Similarly, any life forms beneath Europa's ice shell might be insulated from radiation, suggesting a habitable environment despite the radiation-rich surface condition. Extremophiles also inform astrobiology about the potential metabolic pathways life might use. Chemolithic autotrophs, organisms that derive energy from inorganic compounds, suggest that extraterrestrial life might not rely on sunlight, but could harness chemical energy through processes like methanogenesis or sulfur reduction. This is particularly relevant for subsurface environments in the solar system, where sunlight does not penetrate, and chemical energy from hydrothermal vents or rockwater reactions could sustain life. The study of extremophiles continues to drive the development of instruments and missions designed to detect life in extreme environments. For instance, the upcoming Europa Clipper and Mars 2020 missions are equipped with advanced analytical tools specifically designed with insights from extremophiles in mind. These tools aim to detect biosignatures such as specific molecules, isotopic ratios, or the presence of certain minerals that are commonly associated with life. Extremophiles on Earth have significantly expanded our understanding of the potential for life in the universe. By demonstrating life's resilience and adaptability, they provide valuable models and analogues for potential extraterrestrial habitats, guiding our search for life beyond Earth and informing the design of missions and experiments aimed at uncovering life's potential interplanetary presence. The possibility of silicon-based life forms is a fascinating topic that pushes the boundaries of our understanding of biology and chemistry. While carbon is the foundational element for all known life on Earth due to its versatility and ability to form stable, complex molecules, silicon presents an intriguing alternative. This is largely due to silicon's position directly below carbon on the periodic table, leading to some chemical similarities. However, the arrangement of silicon's electrons and its chemical properties also pose significant challenges. One of the compelling arguments for the potential of silicon-based life is that silicon can form 4 covalent bonds, similar to carbon. In theory, this allows silicon to build complex molecules that could serve as the basis for biological structures. Silicon can also form a variety of compounds with other elements, including oxygen, nitrogen, and hydrogen, which are essential for life as we know it. However, several significant challenges complicate the idea of silicon-based life. 1. ***, bond, strength and stability ***. Silicon-silicon bonds are generally weaker than carbon-carbon bonds, making large, stable macromolecules more difficult to form. Silicon also tends to form strong bonds with oxygen, creating stable, solid silicates rather than flexible, dynamic molecules that can support life's complex chemistry. For example, while carbon-based molecules like proteins and nucleic acids can easily rearrange and interact dynamically, silicon-based molecules might not have the same flexibility. 2. *** silicon dioxide, SiO2, versus carbon dioxide, CO2. ***. When carbon is oxidized, it forms carbon dioxide, CO2, a gas that can easily be exhaled by organisms. In contrast, oxidized silicon forms silicon dioxide, SiO2, commonly known as silica or quartz, which is a solid at Earth-like temperatures and would be much more difficult for a living organism to expel or manage. This solid state of SiO2 makes it less suitable for the biochemical cycles necessary for life. 3. ***, chemical reactivity. ***. Carbon forms a vast array of compounds such as sugars, proteins, lipids, and nucleic acids, which are essential for life. Silicon, while capable of forming diverse compounds, does not match carbon's versatility in forming the complex and stable molecules required for the diverse biochemical processes of living organisms. 4. ***, environmental constraints. ***. Silicon-based life might require environments with conditions vastly different from those we find familiar. For instance, potential silicon biochemistries might be better suited to hotter, drier environments where silicon compounds remain more stable. Alternatively, environments with different solvents, such as ammonia or methane, could perhaps facilitate silicon-based biochemistry, as seen on Titan, Saturn's largest moon. However, no such silicon-based life has been observed. Despite these challenges, the possibility of silicon-based life is not entirely ruled out. The concept encourages scientists to keep an open mind about what forms life might take in different chemical and environmental conditions. Fiction and scientific speculation have often toyed with silicon-based life, from crystal-like organisms to hypothetical biochemistries in extreme planetary environments. Such discussions underscore the adaptability and resilience characteristic of life, potentially even beyond carbon-based frameworks. Ongoing research in astrobiology and exoplanet studies helps broaden our understanding of potential life-supporting environments. Missions such as the James Webb Space Telescope aim to analyze the atmospheres of exoplanets for signs of life, looking for unexpected chemical signatures that could indicate non-carbon-based biochemistries. Ultimately, while carbon remains the most probable basis for life as we know and understand it, the exploration of silicon-based life expands the scope of our search for extraterrestrial life. It reinforces the necessity of looking beyond our terrestrial biases and considering a wider array of possibilities in the ever-intriguing quest to understand life in the universe. Detecting technosignatures, evidence of technology or technological activities that might indicate the presence of advanced civilizations beyond our planet, is a compelling approach in the search for extraterrestrial intelligence. Technosignatures include a broad range of possible indicators, each requiring different methods and instruments for detection. Here are some key technosignatures and how we might go about finding them. 1. Radio signals ***. One of the earliest and most traditional methods involves searching for narrowband radio signals. Given that radio waves can travel vast distances across space with relatively little interference, they are a prime candidate for communication attempts. Scientists use radio telescopes to scan the sky for unnatural patterns or signals that could indicate intelligent origin. The Allen Telescope Array and the Green Bank Telescope are examples of facilities that conduct such searches. 2. Optical signals ***. Another method is to look for powerful laser pulses that might be used for communication or as beacons. Highly coherent light from lasers can stand out against the background of starlight. Instruments like the Laser SETI project aim to detect such signals by scanning large portions of the sky and looking for brief, bright flashes of light at specific wavelengths that could indicate laser activity. 3. Dyson spheres ***. Advanced civilizations might harness the energy of their stars by building megastructures like Dyson spheres or swarms, which would partially or completely enclose a star. Detecting such structures would involve looking for unusual infrared signatures. A star surrounded by a Dyson swarm would emit less visible light but more infrared radiation, as the starlight would be absorbed and re-radiated as heat. Infrared surveys like those conducted by the WISE, Wide Field Infrared Survey Explorer spacecraft, could potentially identify such anomalies. 4. Artificial satellites and space debris ***. Observing other star systems for unusual concentrations of artificial satellites, space debris, or even entire space habitats could provide clues. Using high-resolution imaging and spectroscopy to detect unusual objects or reflections moving in non-natural orbits could signal an advanced civilization's activity. 5. Industrial pollutants Advanced civilizations might produce atmospheric pollutants that can be detected over interstellar distances. For example, certain chemicals such as chlorofluorocarbons are industrial pollutants that do not occur naturally in significant quantities. Spectroscopic analysis of exoplanetary atmospheres, searching for signatures of such compounds, could indicate industrial activity. The upcoming James Webb Space Telescope and future telescopes could play a crucial role in this endeavor. 6. City lights On planets with significant technological development, nighttime city lights might be detectable. These would appear as non-natural, non-periodic brightness variations on the dark side of a planet. Detecting such lights would require very sensitive instruments capable of distinguishing the faint glow of artificial illumination from the planet's natural light. Projects like the Extremely Large Telescope or similar high-resolution instruments could potentially identify these anomalies. 7. Mega engineering projects. Large-scale engineering projects like altering the light curve of a star, for example, starshade or stellar lifting, could also signal advanced technology. Observing unusual or repetitive patterns in the dimming and brightening of a star's light would suggest large structures or activities altering the starlight. Long-term monitoring of star systems using missions like TESS, Transiting Exoplanet Survey Satellite, and future space observatories could help detect these phenomena. 8. Interstellar probes. The detection of interstellar probes or Bracewell probes, autonomous spacecraft designed to seek out and communicate with other civilizations, could indicate intelligent life. Such probes might emit signals or be detectable by their propulsion methods. Current and future space missions might detect these objects if they pass through the solar system, as was done with the object Oumuamua, though no technosignatures were found in that case. The search for technosignatures is inherently multidisciplinary, requiring advances in astronomy, physics, engineering, and data analysis. It also necessitates collaboration across global scientific communities and strategic use of telescopes and observatories. Enhanced computational techniques, such as machine learning and artificial intelligence, are increasingly relevant, enabling efficient analysis of the vast datasets collected in these searches. As we continue to refine our methods and develop new technologies, the prospect of detecting technosignatures remains an exciting and rapidly evolving field, offering the potential for one of humanity's most significant discoveries: evidence of intelligent life beyond Earth. Panspermia is a fascinating hypothesis positing that life, or the precursors of life, can be distributed throughout the universe via natural mechanisms. This concept challenges the view that life must originate independently on each planet where it is found. Instead, panspermia suggests that life might spread from one location to another, facilitated by interstellar objects, radiation pressure, or other cosmic events. There are several variations of the panspermia hypothesis. 1. Lithopanspermia***. This form of panspermia proposes that microorganisms can be transmitted between planets within a solar system via space rocks, such as asteroids and comets. For instance, a major impact on a planet like Mars could eject rocks containing microbial life into space. These rocks could travel through the vacuum of space, eventually landing on another planet, such as Earth, and possibly seeding it with life. The discovery of Martian meteorites on Earth supports this idea, suggesting that material exchange between planets is possible. 2. Ballistic panspermia***. Similar to lithopanspermia, this form relies on the transfer of microorganisms or spores between planets or moons within the same stellar system. However, it emphasizes the role of ejecta formed by impacts that can travel shorter distances, like from one moon to another within the same planetary system. For example, meteorite impacts on a moon of Jupiter could potentially send microbial life to another of Jupiter's moons. 3. Radiopanspermia***. This hypothesis posits that microbial life or organic compounds could be propelled across space by radiation pressure from stars. The light from a star could exert enough force to push microscopic particles or spores through interstellar space. While the vast distances involved make this process less likely compared to lithopanspermia, it cannot be entirely ruled out. 4. Directed panspermia***. This speculative variation suggests that intelligent extraterrestrial civilizations might deliberately distribute life to suitable environments in the universe, either as a form of exploration or as a means of ensuring life's survival. Panspermia has significant implications for our understanding of the distribution of life. Origin of life. If life on Earth originated elsewhere, it implies that life's biochemical traits might be more universal than previously thought. This would suggest that life could be more common in the cosmos, popping up wherever conditions are favorable. Interconnected biospheres. Panspermia posits that the biospheres of different planets could be interconnected. Discovering life with similar biochemistry on different planets would support this idea and suggest that microbial life can survive the harsh conditions of space travel. Astrobiological missions. Missions designed to search for life, such as those exploring Mars, Europa, or Enceladus, might focus on detecting not just indigenous life forms, but also signs of life that could have been transported via panspermia. Finding microbes that share genetic similarities with Earth life would be a significant indication of panspermia. Research supporting these ideas includes studies on the resilience of extremophiles, organisms that thrive in extreme conditions on Earth. Experiments have shown that some extremophiles can survive in space-like conditions, withstanding high levels of radiation, vacuum, and extreme temperatures. These findings bolster the idea that simple life forms could potentially survive interstellar travel. While panspermia presents a compelling framework for the distribution of life, direct proof remains elusive. Future missions to Mars, such as NASA's Perseverance rover and ESA's ExoMars mission, the icy moons of the outer planets, and further studies of interstellar objects could provide critical evidence. If we find life forms or organic compounds with origins outside our planet, it would profoundly alter our understanding of life's distribution, resilience, and the potential interconnectedness of life in the universe. Planetary habitability is a dynamic and ever-evolving characteristic influenced by various factors over geological timescales, spanning millions to billions of years. Understanding how habitability changes provides insights into the conditions necessary for sustaining life and helps inform the search for extraterrestrial life. Several key processes and events shape planetary habitability over time. 1. Stellar evolution. The life cycle of a star profoundly impacts planetary habitability. As stars age, they undergo changes in luminosity, radiation output, and spectral type. For instance, our Sun is gradually becoming brighter over time. When it was younger and dimmer, the distance at which liquid water could exist, the habitable zone, was closer to the Sun. As the Sun brightens, this habitable zone shifts outward. Eventually, the increasing solar flux will cause the Earth to experience a runaway greenhouse effect, making it uninhabitable. Similarly, other stars' evolving characteristics can either enhance or diminish the habitability of their surrounding planets. 2. Volcanism and geothermal activity. Volcanic activity plays a crucial role in planetary habitability by cycling essential elements and maintaining a planet's atmosphere. For example, volcanic outgassing can replenish greenhouse gases like carbon dioxide, which are vital for maintaining a stable surface temperature. Conversely, excessive volcanic activity can lead to severe climate changes, such as global cooling, volcanic winter, or warming, greenhouse effect. Planetary habitability is influenced by the balance and duration of these volcanic processes. 3. Plate tectonics. The movement of lithospheric plates facilitates important geological processes that regulate a planet's climate and support life. Plate tectonics contribute to the carbon silicate cycle, which acts as a long-term thermostat by regulating carbon dioxide levels. This process involves weathering of silicate rocks, subduction of carbonates into the mantle, and subsequent volcanic outgassing. A tectonically active planet can stabilize its climate over geological timescales, making it more likely to sustain habitability. 4. Magnetic field. A planet's magnetic field shields its atmosphere from solar and cosmic radiation, preventing atmospheric erosion by solar wind. Over geological timescales, the strength and configuration of a planet's magnetic field can change. Loss or weakening of the magnetic field, as possibly observed on Mars, can lead to significant atmospheric loss and a decline in habitability. Conversely, a robust magnetic field helps retain a planet's atmosphere and protect surface life from harmful radiation. 5. Impacts and cosmic events. Large asteroid or comet impacts can cause significant changes in planetary habitability by inducing environmental catastrophes. These events can result in mass extinctions, climate shifts, or even trigger volcanic activities. However, impacts can also deliver essential ingredients for life, such as water and organic molecules, particularly during a planet's early history. 6. Climate evolution. Over geological timescales, a planet's climate can undergo significant changes driven by orbital variations, Milankovitch cycles, axial tilt, planetary rotation, and interaction with other celestial bodies. These changes affect the distribution of sunlight and climate patterns, influencing the habitability of different regions. Earth provides a vivid illustration of these processes. Throughout its history, Earth has experienced several significant climatic shifts, including ice ages, warm periods, and mass extinctions. The Paleocene-Eocene thermal maximum, about 56 million years ago, for instance, was a period of rapid global warming linked to volcanic activity and the release of methane clathrates. Conversely, during glacial periods, ice sheets expanded significantly, transforming the planet's climate and habitats. Mars and Venus also offer insights into how habitability can evolve. Mars may have once had liquid water and a thicker atmosphere conducive to life, but it lost much of its atmosphere and water due to a combination of factors, including its weak magnetic field. Venus, on the other hand, likely underwent a runaway greenhouse effect, turning it into the scorching planet we observe today. Understanding the dynamic nature of planetary habitability helps in identifying potential habitable worlds and assessing their long-term potential to support life. By studying these processes, we gain insights into the factors that can sustain or threaten life over vast timelines, informing both our search for extraterrestrial life and our understanding of Earth's future habitability.